Here can see me. Okay, sorry about that. So, let's see. Okay, Hong can hear me but can't see me. Okay. So you say the link is coming? Let's send that to projector. Wait a sec, what is this? Okay, this looks promising. Okay, I'm only a few minutes behind. So this is part of why I like when you send me a request for extensions, I'm usually pretty lenient because I tend to live my life with like very little slack. so I feel your pain, right? I was drawing the last figure right before I came here, so I wasn't just dawdling. I was like, no, I need a figure for this, but there was no time. You're gonna notice it. You can see if you can see it during the lecture. You'll find like there's some inverters where you're like, those are really funny looking inverters. They're not equilateral triangle. There was no time for equilateral triangles, right? So, okay, so assignment 4 is out. It's due December 13th. Well, as you probably may have figured out by now, if you kind of find December 13th is coming and it's like super stressful, send me an email. I tend to be pretty flexible with these things, but that's a good target so that this doesn't eat up your holidays. It's worth 12% of your final mark. You're doing routing architecture experiments with VPR, so you're basically going to try out some of the experiments that we've been talking about here. VPR, which is part of VTR. Okay, so VTR is this framework that has synthesis, placement, and routing. We're skipping the synthesis part, so we pre-synthesize the circuits to LUTs for you, so you don't have to run that part. So you're just doing the place and route, and you can change a whole bunch of routing architecture parameters in place and route. You don't have to resynthesize over and over again. This assignment, see if this makes people happy or sad. It's less open-ended than assignment 2 or 3, so it's not as time-consuming. I'm reading the audience to see Alex is sad. Okay, so Isidore seems sad. That's happy? Okay. So, yeah, so while you may be going, oh, this assignment's coming pretty late in the term, it's not that hard. So if you want to get it done in the next little while, you can. You should write scripts to automate it. So you could just type VPR and various command line options for a long time, but trust me, you will get bored. So you should write a script to automate this. If you don't know a scripting language, this is a good time to learn one because you kind of need to know one. And my recommendation is learn Python. You wouldn't need very advanced Python to do this, but if you don't know Python, this could be a good motivation to go learn it. How many people here know Python? Does everybody know Python these days? And everybody knows it, or you don't know it? So, okay, so everybody knows it. Okay, so fine, you all know it. So, I learned lots of other scripting languages before I learned Python. I've now forgotten them because things like Perl are like almost impossible to remember. So I like Python a lot better. Okay, course evaluations. So they're due by December 6th. So the last lecture is next week. And course evaluations are due that day. I'll try to make it a super good lecture. So you go, wow, that was a good lecture. Now I feel like giving a good evaluation. Go to Quarkus or look for the link in your email. I know you're always busy, but this doesn't take very long. And it's very useful. I read them, kind of get ideas to how to improve, what worked, what didn't. So obviously there's the numerical ratings, which are useful. But in the free-form input, assuming you have something to say on this topic, this course covers a lot of different things, and I've put various things in and taken them out over the years. Like it's kind of a zero-sum game. If I want to put something else in, something has to come out. So if you go, okay, there's one thing that I really liked, don't take that out, and there's something that you should either put in or spend more time on, that's helpful. Now, if you kind of go like, I don't have any idea on that, that's fine. But if you have ideas on that, that's particularly useful feedback. Okay, background reading from last week. 2 recent Intel FPGAs. We'll talk about these some today. Background reading for next week. So if you haven't submitted 10 of these, or if 1 or 2 of them you're like, I wasn't very happy with what I did, I want to put some extra ones in, you are getting towards the end now. So 2 papers, one an academic one on why should we have more than just programmable routing, hard networks on chip, inside of an FPGA. And this kind of goes through the whole case for why you would do that. And then a very recent, well, the most recent paper on a Xilinx architecture, the Versal architecture, which has a lot of things in it, including an embedded hard knock. Okay, so one of the examples of using this is in fact in here. Versal's interesting. This paper has a lot of different stuff in it. We'll talk some about what's in it today, some about what's in it next week. I'll give some more, even though this will be. There won't be another lecture after this reading. Like, you'll have this reading, a lecture that talks about some of these things. I'll give like a few more papers, 2 or 3 more next week that you can choose to read. If you're like, oh, I don't have my 10 and those look like interesting papers, I'll give you 2 or 3 more that you can submit summaries for. And Amin tells me he's really enjoying like marking them. So just for Amin over the holidays, extra options for reading summaries. So. Okay, so we ended last class talking about direct drive. So we had that Lemieux and Lewis paper that said, somewhat surprisingly, we can switch to these direct drive switches that are all multiplexer based. They're electrically very nice, no tri-states. All of our switching is done at sort of low capacitance nodes, so you can use smaller pass transistors to build those. But it had this really major restriction on your routing pattern of you could only drive a wire at one spot. And surprisingly, that restriction wasn't too bad, and it overall worked really well. Okay, so this is work that was done industrially basically at the same time at Altera. And the paper on it is about the Stratix routing and logic architecture, and there are many variations of Stratix now at this point. But they all inherit the majority of the routing architecture that's in HIS. They tweak it, they've changed it since, but the fundamental design of it came from this paper. Okay, so much like that Lemieux and Lewis paper, this paper looked at, well, how many of these direct drive switches should we have? Electrically, they look really good. And what this plot is showing is what fraction of our wiring is direct drive. Okay, so out here at 1, that means all of the routing switches are direct drive, which means they're multiplexers built out of pass transistors, and then they go into actually a pair of inverters. So those pair of inverters, first one's small, second one's big. You get a nice powerful buffer, and it doesn't load these switches much, so we can keep them small. So that's what direct drive looks like. And again, it comes with that limitation of now I can only have one place where I drive a wire because I can't turn this off. So if I put another buffer on it, they just fight, right? I haven't made a routing wire, I made a power waster. So that's not good. On the other side of this, over at 0, I don't use any direct drive switches. What I use instead is a mix. I use half pass transistor switches. So these are big pass transistors because they're hooking together routing wires, which are fairly large and capacitive, so they're a lot bigger, even though they look similar to this. And half of this kind of tri-state. So it's, again, a pair of inverters, one small, one big, and then big pass transistors that allow me to essentially connect this to various routing wires. But they have to be a lot larger because they're driving highly capacitive nodes. Okay, so what do we see from this? It matches what Lemieux and Lewis found, but it's presented in a different way. So for speed, and then the 2 curves are for 2 different routing architectures. So one of them uses a mix of length 4 wires and length 8 wires, so mostly length 4, where you go 4 logic blocks, and then you have to go through one of these routing switches to keep going, but there are some that are length 8, or a mix of length 4 and length 16. So they both show a similar trend. Basically, as I go, this is the average critical path delay of my a bunch of designs. As I go towards more and more direct drive circuits, the chip gets faster, okay? And it gets most of the speed when you just added a few direct drive switches. But it doesn't hurt to just go to all direct drive. In fact, it helps some, right? I just keep getting faster. But most of my speed comes early on when I've just added that's 20% of my switches are direct drive. Why do you think I get most of the speed right away? What do you think happens?
I think that the router is basically going to make your critical path go through direct drive switches, and whatever current critical path
Yeah, so that's a good answer. So for those online, Isidore is saying basically, this is a sign your router is pretty good, right? Actually, I helped write this router, so I'm going to take it as a sign the router is pretty good. And because if it was essentially randomly using these faster switches, you would expect a linear line, right? It's just the probability. If I got half direct drive switches, I use them half of the time on my speed limiting paths. But it actually does quite a bit better than that. So it gets most of the speed right away, but it just keeps getting better at a slower rate. So from a speed perspective, this is an electrically superior switch, and it looks good. Just convert everything to them. Okay, what about routing channel width? And again, we've got the same plot here over at 0. I have no direct drive switches. I've got this mix of tri-state buffers and pass transistors. Here I've got all direct drive switches. And the answer is a little different here. If I have just a mix of length 4 and length 8 wires, so mostly length 4, but some length 8 to get a bit better speed for long distance wiring, there's no strong trend. My channel width doesn't really change much at all. If I use somewhat longer wires, so still mostly length 4, but now some length 16s, then there is some trend, right? As I go towards more direct drive switches, I do need a somewhat wider channel, but it's not that much wider. It's maybe, 8%. It's not huge. So this is a little bit surprising, right? What this says is that switch pattern limitation of you can only drive a wire at one point, surprisingly, is not that bad. Seems like it would be super bad. Now we do have some flexibility about at that one point, how big do we make these muxes? These pass transistors aren't that big, so we can make these muxes a little larger, and that can help compensate for this restriction. But it is a little surprising that it works so well. So yes, it's one of the times when we were actually pleasantly surprised by the result. We're like, well, that's better than we expected. Usually when you're engineering something, the results are always worse than you expected. You're like, I thought this would work really well. It doesn't work that well. Got a whole bunch of work to do. It's going to be a hard weekend. This was like, what do you know? Why do you think that using longer wires, the channel width does have some trend to go up? What do you think? Yeah.
One explanation may be that you need a bigger buffer to drive those longer wires, longer capacitance.
Well, this isn't area. This is just literally how many routing tracks do I need? How many routing wires do I need per channel? And you see this says channel width plus 20%. This is because the way this experiment was done is very similar to what you're doing in assignment 4, where we actually ran the CAD tools to find the minimum amount of routing we needed, and then usually you build a chip with more than that, so we added 20%. In assignment 4, you do something similar, but you add 30%. Yeah, why do you think it happens?
Is it because the direct drive can't be bidirectional?
Yeah, as your wires get longer, this restriction that you only have one drive point becomes more severe.
Yeah.
If you don't want to drive that wire, in this direction from this point, it's useless. And for short wires, that restriction doesn't seem to be that bad. But as you get to like increasingly long wires, the probability that it's going the wrong way or the drive point is not where I need one becomes higher, and you do start wasting somewhat more. So direct drive's good. On the longest wires, it's got a little more of a trade-off. But this is still a surprisingly good result. Again, indicates that the router is able to make good use of this. Okay, so then this puts together, what about area, right? We don't really directly care that much about channel width. We care about area. Channel width affects area. If we need more routing wires and more routing drivers, that's going to tend to increase area, but it's not the only thing. Okay, so by now you know the axis. So this is the routing area. So we're not including the logic block area because it's just a constant. So it's just the routing area averaged across these designs. And here's no direct drive, here's all direct drive. And again, we're doing it for our mix of length 4 and length 8, and our mix of length 4 and 16. They both show the same trend. Basically, your area goes down actually pretty significantly. Like, this is a pretty large drop. So we've saved something like, over 20% area, maybe close to 25% area by doing this, which is a really big improvement. And it just keeps getting better as you add more direct drive switches. So what it means is, well, this length 4, length 8 combination, we didn't really need many significantly more routing tracks, so we have a more electrically optimized design that doesn't take as much area. We use small pass transistors. It just cuts area. It cuts it by a lot. Even with the longer wires, where our channel width went up some, it's still, the electrical improvements are enough that we still save a lot of area. So it's overall very good. And I guess I've already told you this, right? So Lemieux found it improved delay by 9% and area delay product by 32%. The results in the Stratix paper are broadly in line with that. You know, the exact numbers may not be the same. So in Stratix, it went all direct drive. And then Xilinx, the next generation, they had some direct drive before that. So they were clever. They figured out this kind of switch was good. But they used a mix. And then the next generation of their chip after Stratix, they also went all direct drive. So this became the dominant switch. In some recent architectures, it's backtracked a little bit. Okay, so long wires are getting essentially more expensive. I'm going to show you a couple pictures that indicate why. To go a long distance without routing switches, you have to go high in the metal stack because that's where you can make wires that are quite wide and they're manufactured to be quite thick. So the combination of those two things is their resistance is pretty good. And that's what allows them to go a significant distance quite quickly without extra routing buffers. But you can't build very many of them because the reason they're fast is because they're not scaled as aggressively. But underneath them, you keep scaling all the circuitry. So the logic blocks get smaller. These wires are not scaling that quickly. So you're always kind of starved for these. There's a lot of demand for them. Yeah.
Is there any benefit to just making those long wires bidirectional and not using direct drive and everything else is direct drive?
That's exactly it. Okay, so these expensive long wires, some recent architectures have actually gone back to basically tri-stating them. Okay, they put tri-states. They still use something that is close to direct drive. They use that nice muck structure of small pass transistors and then a buffer, but they make the buffer tri-statable, which means they can now put a bunch of those buffers on it. So they could drive it from both ends. They could drive it from more than both ends. They could drive from points in the middle as well. And basically, it's because these are becoming valuable. And once they're valuable enough, spending a bit of more area to make a tri-state buffer and paying some extra delay to have a tri-state buffer is worth it because I just can't get more of these and my designers really love them. So yes, there's a bit of a trend back to it's now a little bit mixed. Still direct drive for most things though. Then let's see. Okay, everybody with me? Does that all make sense? Okay. On to the next thing then. Long wires. So this is a picture of the Stratix metal stack, which is 130 nanometers. I don't have a picture of like, I'll go search for one, but I don't have a picture of like, you know, a 7 or 10 nanometer FPGA metal stack. It would be even more extreme. But what I want you to look at is just that the transistor gate is here. Here's a contact to get to the transistor source or drain. And you can see the metal stack. The metal layers are going in orthogonal directions. Okay, so this metal layer, there are a bunch of wires that are coming out of the paper. And in this metal layer, the wires are parallel to the screen, so you just see kind of one wire. And then you see wires coming out again, and this keeps repeating. So what you can see is that these transistors are pretty small compared to the stack of vias that they're driving. And I've got little wires in the lower levels of the transistor stack. So the first few layers are usually used for connections that are essentially inside the logic block, right? Then I start using these layers for, you know, length 2, length 4 wires, the wires that go between logic blocks and logic clusters, well, RAM blocks and logic blocks and so on. But they don't go too far. And then this wiring up here, which is significantly wider, it's also significantly thicker, right? This is the thickness of it, and you can see that is a lot thicker than these wires down here. So that's the high-level metal. It's got the lowest resistance, and its capacitance isn't really worse either, because while the wires are wider, they're also further apart. The spacing's increased, so that basically keeps their capacitance per unit length constant. So these wires are faster if you have to go a long distance, but I can't build as many of them. And to get up to them, I have to go up through a whole bunch of other vias and wiring. Okay, so that adds some resistance, it adds some capacitance, it adds some blockage to these other layers of metal whenever I do that. It makes it more difficult for me to use them for other things. And as I said, this is getting more extreme. If I was to do this for 10 nanometers, basically I'd extend this figure up by several more metal layers, which would be even thicker looking. Okay, so long wires and direct drive are a bit problematic because we can only have one drive point per wire. But as I just mentioned, that means some of the most recent chips go back to tri-states on these. Yeah.
Actually, a quick question on the last figure.
Sure.
Your switch block can go from a length 4 to like a length 8 or 16.
Yeah.
So if I wanted to do that switch, would I have to go down the metal stack to the switch block, which is in a transistor, then all the way back up to the highest level?
Yeah, you do. Because in an FPGA, the switches are transistors. Which means you go, well, like in an ASIC, you could say, well, I'm going to use some of this metal layer, then I'm going to use some of this metal layer. I'm just connecting them with vias. In an FPGA, if I need to connect those with a programmable switch, I got to drop all the way down to get to transistors. That's my mux, and my buffer, and so on. And I got to go all the way back up to where I came from.
Gotcha.
So there is a bigger via stack to get up and down from these upper level metals. So yeah, it's a good question. Okay, so I guess this is what I've been talking about. Essentially, for all the reasons I just mentioned, it's hard to get on and off the longest wires and get onto the blocks. So the solution to this, well, what would you do? Okay, so basically, if I do the usual thing and I just say a bunch of logic blocks can drive a certain, length 16 wire, say, and it's direct drive. We've only got one drive point for it. So only a few logic blocks that are right near there would be able to get onto that wire. And then if I need to connect it up to a bunch of different, maybe it's for a high fan-out net. If I need to connect it up to a bunch of output blocks, I need via stacks all over the place to bring signals down from it to get into the muxes that get me to pins. Which sounds kind of bad, right? So what do you think? What would you do?
Segment your routing connectivity patterns so that you have basically a hierarchy. So you'll have the short wires will connect to the longer wires, which will connect to the even longer wires perhaps.
Yeah. So I'll repeat that for people online. So Isidore said, well, think of routing hierarchy again. Don't connect straight from the blocks, like the output connection block, to these really long wires, because it's going to make them hard to use. Only a few blocks near their start can drive them, and you're going to have to drop via stacks all over the place to be able to get back into blocks. So build a hierarchy where the short wires basically connect to the long wires, and then the short wires can connect to blocks. So you have to go from blocks to short wires. Maybe that gets you far enough. You just come back into a block. If you have to go longer, you go from the short wires onto the long wires, and that's kind of like your expressway. And that's exactly what was done in Stratix, and all the follow-on Stratix devices do this, and then Xilinx, at some point, they did different things, but now they do something similar to this too, okay? So this exact pattern will vary from one chip to another, but the basic idea is used very extensively now. Yeah?
Does that necessitate the introduction of length 0 wires so that you can get directly onto a long wire without artificially going to the left and then back to the right?
Okay, so the question, so Isidore was asking, do you need length 0 wires, which are essentially just muxes that, you have a mux that doesn't really go anywhere. Its output just connects into other muxes. Sometimes those are called length 0 wires in some routing architectures. I guess it doesn't strictly necessitate it, but as you start getting expensive resources like these long wires, it becomes kind of desirable to make it easier to get on them. So you might go, well, I'm going to have a few muxes, and those muxes don't directly drive a wire. They just drive another mux that drives a wire. And essentially, it's a way to get more options of how do I get onto this expensive resource. So you don't have to do that just because you have long wires, but having an expensive resource like long wires does make them more desirable. So I can't remember if we did it in Stratix, but we did do that for the long wires in some of the later generations. I'm not showing that in this figure because it's kind of a detail. It is effectively, you can think of it as a length 0 wire. Like just basically you have the mux, but the mux doesn't really go anywhere except to other muxes. But it serves a similar purpose of sort of giving you more ability to collect signals so that more of them have the option to get onto some expensive resource. Okay, so how does this work in Stratix? Okay, so if I want to go from a logic block here to another one that is, say, 4 units away, or I guess this one's 3 units away, I can use my output connection block switches to just directly connect into the mux that is that direct drive point for this length 4 wire. That signal goes along the length 4 wire, and the input connection block is a mux that allows a bunch of wires to go into a block. It has connectivity for some of the mux inputs to these length 4 wires, so we can get it. So for the shorter wires, we just go straight out from a block onto the wire, straight back through a mux into the wire. But if I want to go a longer distance, I'd like to use one of these long wires, or maybe a bunch of them in series. So these long wires are high up in the metal stack, and in Stratix, the horizontal ones were 24 blocks long, the vertical ones 16. Why are they different? It's because the layout of the logic block wasn't square. So the logic block is taller than it is wide. So basically this 24 is close to electrically optimal. What I mean by electrically optimal is for any wire, there's a certain distance you go along it where the resistance has built up enough that you're better off to go through a buffer rather than to keep going. And that break point was around 24 units for the horizontal wires, but because the logic block's taller, it's around 16 blocks for the vertical wires. So that's what set these 2 different lengths. There's basically not much. If you go shorter, your wire's not as fast for going long distances because you have to go through an extra buffer and programmable switch. But going longer is no longer gaining you anything. And at a certain point, you start losing. Like it's actually better to go through a programmable switch and get the rebuffering than not. So that's why these aren't like 50 or 60 long. They're also harder to use. If they're 50 or 60 long, you basically are more prone to wasting wire. So if you're not getting any speed for doing that and you're more prone to wasting wire, it's like doubly bad, right? So these are chosen to be near the electrical optimal point. Does that make sense? Anyway, but you can't directly, to minimize how many via stacks need to go up to these things, to make these scarce long wires more usable, they can't be driven directly from the blocks. So if I would need to use one of these long wires, I first come out from a block onto a length 4 wire, and the bunch of length 4 wires that pass near the drive point of that length 24 feed into its routing mux. So they're all options to get onto it. So I get onto this long 24 wire. I can get off of it at the end, and I can get off of it at a few points in the intermediate points along the wire. So there are a few via stacks, but not like every single channel or logic block. So I can get off of it, and I can drive straight onto a length 16 wire. So the long wires can drive each other. And then to get into a logic block, I have to get off that long wire network back onto a length 4. So the long wires can drive the short wires as well. And then those are the ones that go back into the logic blocks. Okay, so it is a form of routing hierarchy. To get to the long wire network, you have to get on the short wire network first, and to get to the logic blocks, you have to get off the long wire network back onto the short wire. It makes these expensive resources a lot more usable. Yeah?
In order to ensure a homogeneous switch pattern, does that mean that we're going to have a multiple of 16, width for the track, like the trunk, whatever you call it?
Yes. So in fact, so basically what Isidore is saying is like when you actually go to make the layout of these things, you want to make FPGAs that you buy from AMD or Intel were basically laid out with full custom, meaning like blood, sweat, and tears by a whole bunch of layout engineers. It's really expensive, but they hand optimized the sizing of various transistors and created custom layouts for a tile. I mean, you can't do that for a 4 billion transistor chip by hand. What you can do is you can take a logic block and all the routing that goes with it, and you can hand lay that out. And they actually have some tools to help them. So even that is hard enough that there's some tools that help them a bit. But once you do that, you can repeat it. For that to work, you need to have a repeatable pattern. So for a repeatable pattern, what you do is, this has got a length 16 wire in it. What you can do is say one length 16 wire starts here. So there's one direct drive switch. And a different one will start at the tile above and so on. But basically, you couldn't have 12 of these, right? You could have 16, where you say one of them starts in every single tile, and I'll lay out a tile where that happens. You could have 32, because you could say two of them start in every tile. But I can't have 12, I can't have 17, etc. And yeah, that is a restriction. If you look at certainly any of the Intel chips, I think the Xilinx ones or AMD ones are the same, you'll find that the number of wires is divisible by its length. Okay, so the number of length 16 wires is divisible by 16. In Stratix, we had essentially one bundle, 16 of these and 24 of the others. And then we found that these were the resources that tended to get used up first. So in the next generation, we doubled it. But to double it was, challenging to find enough high-level metal. But it was doable. To quadruple it and so on probably isn't doable. Like there's not without adding a bunch more metal layers. You can add more metal layers in the manufacturing process, but it makes your chip more expensive. The executives don't like more expensive chips. So this is like a random aside, but so after my third daughter was born, I took off like 6 weeks for paternity leave, and that corresponded to when the senior managers meeting was in San Jose for Altera. So every year they bring all the director and above employees down. So I didn't go. I'm off. And then one of my Dave Lewis, who was on my team, and he was an architect, which is considered equivalent to a director. So he went to the meeting, and he came back and he said, "Yeah, so John Dana, the CEO." In his talk to the company, he focused on number of metal layers, right? He goes, "We use so many metal layers, our chips are so expensive, we don't need so many metal layers, I want you to cut the number of metal layers," right? And my boss told me this too, right? He's like, "Yeah, John Dana really wants to cut the number of metal layers. Why are you guys using so many metal layers?" And Dave Lewis was basically like, "Yeah, I mean, whatever, obviously we need them, like who cares? I'm just ignoring that." But I was starting to get asked this question by more and more people in the company. I go, "Dave, you need to do a study showing that you use these layers effectively." He goes, "That's a waste of time." I go, like, "Dave, like the CEO has chosen you as his example of high cost. You need to make this study." He goes, "I know the answer to that study. It's good." I go, "I don't care." Like, you need to make that answer known now, because this is developing enough momentum that we're pretty rapidly going to wind up with the next chip has fewer metal layers because the CEO said so. So anyway, he did the study and it ended it. But yeah, so it was interesting. It was like my value add on coming back from paternity leave was to get Dave Lewis to do a study that he thought was completely pointless, but I am pretty sure had a point, right? So, okay, so what did we do in this chip? So the backbone of it was length 4 wires. 71% of the routing tracks are length 4. Some length 8, so 17%. And then about 12% of the routing wires are these longer ones, which are hierarchical, where you can only get them from the short wire network. And you can only get to the length 4 wires at sort of certain points along the wire. Like basically at every 4th spot in this particular chip, we would drop a via stack, and that reduced the loading and made layout a lot easier. Okay. It'll be not bad, actually. So we're not using the same process technology as Stratix, and we're not, to keep the runtime small in Lab 4, I'm giving you relatively small circuits. So if you were to publish a paper, they would go, "Why are you not using bigger circuits, etc.?" And they'd be right. But basically, we're just using smaller circuits so that you guys don't have to sit in the lab waiting for things to run for a really long time. Those two changes mean that you won't necessarily get the same answer. Also, you can't assume that just because it was done in industry that it's necessarily optimal. Like, I just told you, like, that is a real story about how do we choose how many metal layers in our chip, right? So the CEO thinks too many, you should cut them. Much of our executives go, "Yeah, it's too many, why don't you cut them?" I tell Dave Lewis, "I don't think this is too many." He says, "No," so I get him to prove that, so we don't cut them. Like, decisions in a company are not like some global convex optimizer that figured out the global minimum. Sometimes they're that chaotic. So maybe you'll come up with something better. So, okay, so let me show you one thing. This is the only data I know of that's like this. So Stratix was the architecture that came out of the acquisition of RightTrack, a startup that I created to commercialize my PhD research. And we were redesigning Altera's CAD tools, and we convinced them we should redesign their chips too. So it was a big change. They had always done various types of hierarchical FPGAs. The way they did hierarchical FPGAs wasn't as strict as the sort of classic academic ones, so they had some enhancements that were beyond that. So they acquired us, and we built Stratix, okay? So a different style of architecture. But you're a big company, and this is a major decision, so they didn't really trust that they thought maybe we know what we're doing, that's why they bought us, but maybe we don't, it's not 100% clear. So they still had another architecture team that made the next generation of their hierarchical FPGAs in the same process node. So these are both 130 nanometer chips made by the same company, same IC design department, et cetera. So it's a very head-to-head comparison. And they're both supported in Quartus, and you could actually just compile to one and compile to the other. So it's the only really head-to-head comparison I know of island style versus hierarchical, where it controls for most of the variables. And these are like the smaller designs. This is 130 nanometers, so these designs would be, these are like maybe 30,000 lookup tables. These are maybe 150,000, and these are maybe like 400,000, okay? So it gives you some idea. So nowadays, this would be maybe medium, and these would be small. Everything's kind of shifted to the right. This is like circuit by circuit, what performance improvement did we get with Stratix, like its island-style architecture versus Apex 2, the hierarchical-style architecture. And it was a lot. It was, from 38% for the smaller designs to an average of 60% for the bigger designs. And clearly, the bigger designs, are the future, right? It's going to be even bigger ones out here. So it was, if you average this, it's 40% faster, but if you weight it towards the biggest ones, even more. Not shown on this plot is that at the same time, it was 30% smaller. So if you multiply, the area delay, this is twice as good, which is a big improvement. Like twice the area delay, cutting the area delay product in half basically makes the chip twice as efficient. So that's a very big improvement. So it's a demonstration that at least for big designs, going hierarchical all the way just is not as efficient as island style, because that's the biggest single difference between these things. Yeah. Yeah, it was released. It was nowhere near as successful as Stratix, because it's nowhere near as efficient. So Stratix was the future. That's why there's a Stratix 2 and Stratix 3 and 4 and 5. And then Aria 10 is really Stratix 6. And then they went Stratix 10. And then they went Agilex. So, but they're all effectively based off this architecture, right? Just every once in a while, marketing, I don't know. Like marketing likes to build a brand for a while, but then at some point in marketing, it appears you're like, to justify my existence, I better rename some things. So Altera eventually renamed Stratix Agilex, and Xilinx renamed Vertex into Versal, right? So I don't fully comprehend when you have a strong brand, but it does appear that there's a motivation of you do have a marketing department that needs to justify its existence. So renaming things can be part of that. But yeah, there was no Apex 3 because this was done, it didn't sell very well, it wasn't nearly as competitive, it became clear what was the path forward. So from a comfort perspective though, this was probably pretty reasonable. Like if you think about the world at the level of a CEO or COO, they actually, I think Altera's management made some fairly clever, it's a fairly gutsy call to go out and buy a company and say, let's try a new architecture. It's maybe too gutsy though to say I have no backup plan. So it was, even though this chip wasn't successful, it was probably a very logical decision because it might have gone the other way, right? Okay, so a few more routing architecture principles. So moderate length wires are kind of your workhorse. So length 4 has been a very good length of wire to use for a long time. Metal resistance is gradually going up per logic block, which means there's some trend in the most recent chips to have your workhorse wires be a bit shorter. But if you were to take a guess of what's a good routing wire length, 4 is pretty good. Scrambled or irregular switch patterns tend to work well. Like highly regular ones can actually have more blockage. But that said, highly regular ones sometimes lay out well. So probably the best pattern of all is one that does some scrambling, but it does it in a way that it's not so scrambled it's really hard to lay out. It just gives the router lots of choices. Your router is always searching for paths. Okay, so all paths start at the output of some block. They go out into wires. Usually your wires connect to more wires. And eventually they need to get back in some block. And that's normally you go into a logic cluster or logic block. So there's some muxing to get into that. There's usually some local interconnect inside of it. And then you actually get to the primitive, right? The lookup table or the RAM core or the multiplier input. So there's always this cascade of decisions or switches that get turned on. So when you're building routing paths, you kind of want to avoid flexibility choke points. Okay, so what I mean by that is, let's say I made it really hard to go from, I made this really lots of switches to go from block outputs to wires, lots of switches to go from wires to other wires, but then I decided I wouldn't make very many switches to go from wires to logic cluster inputs. That's where I'm now going to get most of my routing blockage. It's going to be my biggest problem. I could try to compensate for it by adding, even more wires, even more switches over here. And I can do that, but generally I'll have to compensate for it by putting a lot more flexibility in these other things. What I'm better off to do is find that this is the choke point, right? I didn't put enough flexibility there and add more flexibility there. Okay, so you kind of want, you're thinking of this as a cascade of decisions that together give me enough flexibility to make this path without it being blocked by other ones. And where I have the least flexibility is usually the most efficient place to add some more switches to reduce routing blockages. So that means try to avoid choke points. You also want to avoid excessive flexibility. So it means if I already have a lot of, for example, flexibility going from the block output to wires, well, if I have lots of that, some of it's probably wasted, right? Like I just get very little routing blockage there. I could probably rip some of those switches out and I wouldn't notice much degradation. So you kind of want to balance this. Okay, so what does that mean? So one of the things it means is it's very useful to make your block to routing interface similar for all blocks. Okay, so let's take a logic cluster, and let's take an Intel style one. You go from a logic cluster input through some local routing, and Intel uses basically some form of either fully populated or more commonly partially depopulated crossbar as this local interconnect, and then you go to a LUT input. Okay, so you do that for your logic blocks. There are studies that show that that works well. The local routing lets you capture some signals without them even leaving the logic block, so that's good. Some signals have fan out, so it comes into the logic block once, gets distributed to multiple LUTs, so that's good. Okay, let's think about RAMs now. Okay, so this was to get into a logic block. Now I want to get into a RAM. Okay, so in a RAM, local interconnect, well, do you think local interconnect is as useful in a RAM or not? I should use the Socratic method more. What do you think? So one of the uses of the local routing inside of a logic block is you have some LUT outputs or BLE outputs that feed back to other ones. Do you think that's going to happen in a RAM? Okay, so I see people shaking their heads. Yeah, it's kind of bizarre. It's hard to think of what that is. Like I look up some data and then that data becomes my address, or is it becoming my data? Like what is that? Like it's a bit weird. You go, well, I don't know, maybe it's some kind of pointer chasing, but it's kind of hard to get your head around that. So yeah, that's not going to happen a lot. Whereas in logic, it happens all the time. This lookup table feeds another lookup table. Yeah.
So you may still want to have some amount of permutability among your inputs, though, which you do get from the local crossbar.
Okay, so you're agreeing that it's not as useful for capturing, outputs feeding back to inputs, but you're saying I still want it.
Yeah, well, I still think it would be useful for permutability among your inputs.
Right, and I was actually trying to lead you guys down one path, right? But Isidore's refusing to be led down that path, so kudos to his intellectual strength. So Isidore is saying, well, yeah, despite that, and also fan out is not as common either in a RAM, right? So in logic blocks, I might have some enable signal that goes to all the LUTs. In a RAM, I'm not going to take it's unlikely I'm going to take some data bit and say, I'll write it in all the RAMs. Like, why am I writing the same data bit into 12 bits in the data word? It's kind of bizarre. So the fan out also isn't going to work as well. But despite that, Isidore's saying, but I still like it because I still kind of like the local crossbar gives me more routing options. Is that right?
Yeah, and I might take it even further. If you look at a lab, right, if you look at a LUTs, right, LUTs themselves are internally permutable, whereas a RAM that's just not true. If you hit the address, the address goes to the wrong thing. You know.
Yeah, that's true. So, okay, so Isidore's also pointing out that a LUT, by changing the truth table, you can say, change my input, which helps the router. It's got kind of one last stage of flexibility that a RAM doesn't have. You can't just change. In a few cases, you can change things, but there's not as much, right? You can't just flip around your address bits and so on, certainly as easily. So you're right. Your data bits you can, but you have to do it for both the read and the write, so it gets kind of messy. Like if you flip your data bits, you could say, I don't really care which bit I write to in the RAM, just write to one of them. That's correct, as long as you make sure you do the same thing on your read path. So yeah, there's some flexibility there, but it's kind of a mess to try to take advantage of. Yeah, but Isidore's got the right idea. Basically, even though at first glance you go, this local routing in a RAM doesn't seem like it's as useful, it does give you this extra ability. If I come in on an input, and I still have one more stage of muxing to go from the cluster input to the LUT or the RAM, like the primitive input. And it's actually a bad idea to take that away from the RAMs or the DSPs. And the reason is you're kind of making your routing problem more difficult to get into certain blocks than other ones. So yeah, what we did at Altera and Intel is keep it as similar as we can across all the blocks. If you have this amount of flexibility in your local routing for a logic block, that's your most common block, try to replicate that in the RAMs and the DSPs and other things. And that wasn't obvious at first, right? So there were some chips where we did do it the other way, and it doesn't work as well, because you just fundamentally can't optimize the routing network as well. So that's one of the things you want to do. The other thing you want to do, I mentioned for PCI Express, we want to kind of keep the maximum inputs and outputs that connect from a block into a piece of channel about the same. So we want the used inputs per channel, used outputs per channel. And by channel here, I really mean a piece of a channel, like you're hooking up to the routing wires right beside you in a specific routing channel. You try to keep that roughly the same. So this is maybe, I mentioned why before, so we'll see how many people can recall back a lecture or two. So why do I want to do this? What's the purpose of doing this? Does anybody remember? Why can't I just hook, like Logic Block hooks up 20 things to the routing channels near it? Why can't I hook up 200 from some other big block? Yeah?
Your general routing pattern is designed for like some amount of routability, and you're going to get hotspots if you try and route too much.
Yeah, it's going to produce a big hotspot. So remember that like the channel width I need is lambda, the number of inputs I need to get out of that channel into some block, times the average distance they went, divided by the fact that there are two channels. So if my lambda varies wildly, like the number of signals I'm trying to take out of a routing channel, or I can reverse this and do it the other way, the number of signals I'm trying to put into a routing channel, if it varies wildly from one spot to another, again, I can't really tune my routing architecture. I either need to make really wide channels for those hotspots, or I just make narrower ones for everybody else and just accept that I'm going to have problems if people use those blocks. I'd really rather not do either. So this is why blocks like PCI Express, we said we should really spread out those large number of outputs and inputs across many routing channels or pieces of routing channels to keep this roughly constant. This is maybe a hard question. What does this mean for partial reconfiguration? So remember, partial reconfiguration means I'm going to take out a piece of my design. I'm not going to shut it down. I'm not going to reset it. I'm going to program in another piece of something else. I'm going to change the function of this module. And I want it to just hook in to everything else that's already there. So does this have implications for how I do that? What do you think?
It'll make it worse.
It'll make it worse. You're just flipping a coin, it'll make it worse. What do you think, Isidore?
Well, I think that, so if you want to partially reconfigure, it means that you have to match like the exact wire coming in and out, connecting the old design to the new components.
Yeah.
And that matching problem is going to be harder if you can't reorient, like if you don't have that local crossbar within the block.
Yeah, that's exactly right. So usually when I'm, like basically all my other routing problems, well, let's go back to slide. A regular routing problem always looked like that. right? Start at a block output, go through some wires, go through this local interconnect, go to an input of a primitive. So you got a bunch of muxing or choices for each one of these steps. And if I do partial reconfig in the most obvious way, which is that I basically say if I take out this, I got some design, I take out this piece, reprogram it, that its interface must be the exact same wires they used to be. Okay? That's a more difficult routing problem. When I actually do the routing of the new thing that I want to stick in here, so I'm doing that offline, but the router has to succeed, it basically, the signals going into it start on wires, not on block outputs. But block outputs can reach a bunch of wires. So just starting on a specific wire is fundamentally harder. And the connections coming out of here, they don't end at a LUT or a RAM, they end on a wire. But we used to have these two stages, well, at least a couple stages of muxing, right? Like get to the connection block as muxes that get me to the cluster inputs, and then I have some local interconnect muxes after that. So I just lost a couple of stages of muxing. That's harder, right? I need to get to some specific wire instead of getting to maybe one of 50 wires that would have made it through that mux network. So it's a lot harder. So the first versions of partial reconfig, which were done by Xilinx, did go straight to wires, okay? And they were harder to route. And in Stratix 5, Altera chips never supported partial reconfig, partly for patent reasons. Actually, there was a patent that we couldn't design around for a long time, but eventually when the patents were cross-licensed, it was like, hey, we can design around this now. Well, we don't have to design around it. Like, the lawsuits are settled. We could just use this idea. We got clever. We basically went, well, we're not going to do that. What we'll do is we will insert, basically for signals that are coming in, we'll always insert a LUT. Okay, so it does start at the output of a block, and for signals going out, we'll insert a LUT as well. So it ends on the input of a LUT. So it's going to look the same difficulty as everything else. If you look at the design, you go, why do I have these like just LUTs that just copy their input to output? And from a logical perspective, it doesn't make any sense. You just added a little bit of extra circuitry. But from a reliability perspective, it's much nicer for the CAD tools. So anyways, we came up with this. We're very proud of it. We're getting ready to ship it with Stratix 5 and market it. And then Xilinx did exactly the same thing in their CAD tools. So it is a good idea. It was like, it's going to be a lot harder to market being the second to do this. So that's too bad, right? So, yeah, this was purely at the CAD level. You just change how the CAD tools work. They would automatically insert the LUTs on both sides, lock them down near the edges, and then basically the routing problem is no harder. So I still remember I saw the Xilinx did this. I was like, oh man, if you just given us like another 8 months, it would have been a great splash of that we've done it better than you. But now there's no possible way to claim that. So, yeah.
So is there any downside to this second solution come up with this one?
The downside is that you've added a LUT. Okay, so adding a LUT costs you a bit of area, it costs you a bit of delay. Yeah, one LUT, it's not that much. Usually your interface is not that big compared to what's inside. You probably should, it does mean that you shouldn't be partially reconfiguring tiny things. It also does add a little bit of delay, so it makes it a stronger case that you should really register on this boundary. But that's best practice anyway. So there's not a huge downside, but there is some, but it helps the CAD tools. End users usually don't really care about the CAD tools. They're just like, so they kind of like, why do you have these extra LUTs? They don't know that the CAD tools would have probably had lots of unroutes otherwise. So they don't appreciate the brilliance of it because you've just taken away a problem they never saw, right? So, yeah.
I noticed that this is an architectural change that had a bad effect on partial reconfiguration. Is it often the case that architectures try to plan for partial reconfiguration?
It's not important enough currently that it's the main thing you do. But it's also not very, as long as you can rewrite, if your configuration circuitry can basically rewrite part of your design without disturbing the other part, then you can basically do partial reconfiguration. And it becomes, so it's not a high cost to support it. It becomes a CAD problem to how do you make that usable by people, which has been the harder problem. There are a few architectures. There's one called the 6200 by Algotronics that was built years ago for partial reconfiguration. It was bigger than other FPGAs, but really easy to partially reconfigure. So Xilinx bought them, but they end of life to that architecture. So I guess that doesn't prove that, you know, architecting primarily for partial reconfiguration is a bad idea, but I guess it doesn't prove it's a good idea either. So I think you have a little bit of chicken and egg. My belief is that partial reconfig is useful in some cases, but it is a more difficult design flow. You can do a reasonable job of it without spending a lot of area on it. And there's no existence proof that spending a bunch of area on it makes it so much better that people would actually buy that.
How long is the overrun to do partial reconfig? Like, 'cause, like, I'm trying to think who would be using this in practice.
I guess one of the cases I gave you, like the one that made us put it in Stratix 5, because you don't put much in your chip without a reason. Yeah, actually, I knew how cheap it was to put in, and marketing really wanted partial reconfiguration. So the generation before Stratix 5, we were getting somewhat late in the design cycle, but I knew that we could put it in with just a change of the SRAM. So I sent that to the VP of IC design, I don't know, and answered marketing saying, yeah, it wouldn't be too hard to add that. Late, not super late in the design cycle, but we're locking down the architecture for Stratix 4. And my boss got super mad at me because I told marketing it wasn't that hard. And he was like, what were you thinking? And as I was sending the email, I was thinking, you know, I don't know if I should tell them it's not that hard, because it's not. But they might then ask for it. And I'm like, well, you know what? It's not my job to tell them you can't have it. Like, if they ask for it now and we say it's the next generation, whatever. Someone, you know, IC Design can just say that. But yeah, my boss got super bad. He's like, don't ever tell marketing it's not that hard. So even if it's not that hard, you don't tell them that. So anyway, I don't know if that answered your question though or not. So
Who are the clients that are using this feature?
oh, okay, yeah. So the key thing that made us put it in Stratix 5 was the high-end communication market. So I think I gave in the very first lecture when I was talking about partial reconfig, or maybe one of the other ones. Yeah, maybe one of the programming model ones. It's like, so this isn't the only use case, but the one that we saw that was significant was called Mux Ponder. You're taking in a whole bunch of data streams from different protocols like DSL, I don't know, Sonnet, some standard with a bunch of numbers in it. And then you're muxing it together, putting it on high-speed optical fibers, so Sonnet with like bigger numbers in it, and sending it across the country. And these kind of expensive core routers had a whole bunch of FPGAs in them. And if they lost a customer, but they gained a different one, and that one has a different protocol they bring in, they don't want to bring down the whole device because it essentially brings down the internet for their customers for a little while. So they had all sorts of extra logic to deal with. Maybe it's this input, maybe it's that input, maybe it's this, maybe it's that. But if you could partially reconfigure it, you could basically take out that customer's, you know, DSL 58 modems and put in this one's Sonnet, you know, 160 input. And that would happen very infrequently. You know, maybe that happens like once a month or once a year or whatever. It's not very often, so nobody cares about, I mean, that customer's getting kicked out. Like the person who is like basically decided I don't want to pay for all this or something. Nobody cares that their stuff's being reconfigured and it's not available for 10 milliseconds. They do care that none of the other ones were disturbed. So that was the kind of the key use case that we saw for partial reconfiguration that was like very disciplined, like slowly changing, a system that had many communication protocols that it would change between quite slowly. There are some other ones like that, but they're kind of like modems where you're choosing your protocol, but these are like super high-end modems.
Way too slow for something like, let's say you have a cell tower where you've got multiple people connecting to it using different protocols potentially, and you're going to reconfigure some core for each client because...
Yeah, that's a good question. I mean, so I don't know. I don't know enough about cell phone protocols to know the answer to that. It depends on how fast that is happening. And then the other thing that always happens is the design flow is more complicated. You're trying to sort of floor plan your design, and you're trying to think in space and time. So if you start thinking, I've also now got 1,000 customers and 20 protocols, like it does get very complicated quickly. These ones are also easier to think about because it's a bunch of high-end customers, not so many things. Does that make sense? But maybe that works as well. I'm not really sure. So there are a bunch of academic works that essentially think of partial reconfig as like virtual hardware. So the idea being like you have virtual memory in your computer, so you need something to be in memory, it just gets swapped from disk into memory. So and partial reconfig in theory could allow that to work, like paging in logic. So there are actually some academic works that try to investigate that. It's very hard to find an actual use case for it though, because the design flow is more difficult, the reconfiguration time is slower. So finding a case where that kind of fine-grained swapping of hardware actually results in a better system has been difficult. Yeah.
Sorry, and I'm taking too much time. But say, what about in the data center where generally, like, clients are coming very quick on and off, but you may say that, like, at this time of day, these type of clients are much more prevalent, and you can just say, like, we have 100 clients using, like, service A, and, 20 clients using service B in the morning, and in the evening it's reversed.
Yeah, that could be a good use case. And in fact, data centers do, I showed you in Catapult, they basically take essentially the periphery of the design where all the high-speed I/O is and so on. And they build what they call a shell, and it's got some management layers, and it simplifies talking to everything. It's all pre-done, it's placed and routed, it's locked down. And then they actually do partially reconfigure what's inside. And what that allows them to do is they can put in different accelerators without taking down like the IOs, which might actually have bad consequences for the system, right? Even if you take out the whole, what is it accelerating? It goes from compression to encryption. You didn't take down the server. And if you basically just completely reset the FPGA and it's actually the path for the server to talk to the Ethernet, you probably took down the server. So that's another very disciplined use of partial reconfig. Okay, so let me talk about a few more principles. So left and right. Which one of these two things is better? L, okay. So yeah, so left is better. Why is left better? So Isidore, what do you think?
That's better because for the reason we said before, where you only have to do like the full custom design. If you are doing rights, you're basically making a different interface for different blocks.
Well, this one, you're right. You can make a tile here. And it's a bit tricky, but you can make a tile that is replicable. I mean, you could, that's a good question. I mean, this one, you could probably do that as well, but you use mirroring. You don't use translation. You make a tile, maybe it's not just one tile. You might have to make this tile and then make a larger tile. So you might have to do that. So you're right, could have some layout efficiencies. Any other reason? Yeah.
If you just look at that red, the one you circled on the left that is red.
Yeah.
If it wants to go left or right, it has the ability of choosing, like it can go to the left by taking the one ahead of it, or it can go to the right by taking the 1 second above. But in the right one, you can only go left, or at least it's really hard to go right or on faster change.
Yeah. So basically, this is kind of like what classic hierarchical architectures have. This is like got a hard boundary. Like it's difficult to go across this cut line, but it didn't like save me any area. I just stagger the start points of the wires, and I don't actually need any more wires. So I've got more choices. Basically, I can make that blue connection only with 2 wires. And on the other side, I can make the red connection and the blue connection with 1 wire. So without any extra area, I've just got more flexibility. Yeah.
So you get a routing hotspot because, like, at that location, everything ends up getting off there.
Yeah, I guess that's one way of thinking of it. Yeah. You've got fundamentally fewer choices. So with the same area, if you can give more choices to your tools, it's better. So try to avoid hard boundaries where wires stop and end in the same spot. So staggering your start and end points of wires is better. And so hierarchical FPGAs classically had what's on the right. We still use hierarchy to group access to rare resources like the long wires. But if you look at the long wire discussion that we had earlier, the long wires are still staggered. Like they are effectively a higher level of hierarchy, but it's kind of smeared out. There's no boundary where all the hard long wires start and stop. Okay, so a few more routing principles, then we'll take a break. Okay, so I said one of the principles of routing architecture is don't put too much flexibility in one of your routing hops. Every route is essentially a bunch of cascaded decisions. Don't put too much flexibility for any of those because you're wasting area. Don't put too little for any of them because that's going to be your biggest problem. And the cluster interconnect that we've studied so far what we studied back in the Ahmed and Rose paper, was fully connected. So full crossbars from your cluster inputs to your LUT inputs or BLE inputs was a full crossbar. From the outputs of LUTs back to, or BLEs back to their inputs was a full crossbar. So it seems like it might be excessive, right? Like there's no chance of a crossbar blocking. So whereas the rest of our routing decisions, they definitely can block. So the question is, can we remove some and save area? And if we do, it might have some knock-on effects. We might have to add some flexibility elsewhere, but hopefully less, and we could save some area. This is another paper by Lemieux and Lewis that looked at exactly that. So this picture is basically the local interconnect inside of a logic cluster or logic block. It's got 4 BLEs, and this is the local interconnect. And basically, a bunch of wires come in from the general routing channels. So they're showing dots where there's a programmable switch. So this is your input and output connection block shown here. Get into my logic cluster, and I have a bunch of local routing wires here. And I also have a bunch of feedback wires, which are here. And wherever I have dots, that's where I have a programmable switch. So if I count up how many dots are in any one of these horizontal lines, that says how big a mux I need. Right? So it's like a 4 LUT. I count those dots, and I need 1, 2, 3, 4, 5, 6, like 7 to 1 mux. Okay? And if I counted all the wires, it looks like it's about 14 wires. So if I did a fully populated crossbar, I would have needed 14 to 1 muxes. Instead, I need about 7 to 1 muxes here. It's going to cut my area, like the transistor area of my local interconnect by approximately a factor of 2. So when they do this study, they leverage the fact that if you're going into a LUT, you don't actually have to hit a specific input of the LUT. The synthesis tool would have chosen some input, like you're going in on LUT A, but you don't have to actually go in on LUT input A. You could go in on B or C or D, and all you have to do is fix up the truth table afterwards. You have to swap. If somebody else was using input C and you use it, well, that one has to go use a different input. But routers that's congestion negotiation. Routers are good at that. So in their study, they leverage that fact. They basically say, well, one of the things that's going to help us take some flexibility out of this crossbar is the fact that we've actually got one last stage of switching. If our router goes all the way up to the point where it chooses LUT inputs. The other thing they do is they say, let's make this input switch pattern the same for every one of our LUTs. Okay? Actually, I think I have that highlighted. Okay? So if you look at those, so I probably should have clicked the button first. So if you look at these patterns, they're all the same. That actually does something nice for you. If all these patterns are the same, it means the router can actually choose which LUT, it can actually switch which LUT does what. It doesn't make any difference of if I got a signal to this LUT, it means I actually could have gone to this LUT as well, or this LUT, or this LUT. So that actually makes my outputs, these BLE outputs, logically equivalent. So you'll see in the VPR architecture file that you've been given, there are these keywords about logical equivalence, and that's actually telling the router, are you allowed to swap these pins or not? With this pattern, we're not only able to swap the input pins to the LUT, we're actually also allowed to swap the output pins of the cluster because we can go into, it has no impact on the router, right? If it got to one LUT, it could have gotten to any one of them. Therefore, the router can choose any output it wants to start the routing of the output signals. Yeah?
Counterpoint. If we kept the entire left part of the pattern the same, except for the line, like except for the small box you see in the second one, then, and you were to just permute that for each of them,
Yeah.
you would still be able to swap any LUT, right? Because you're guaranteed that if you hit 3 pins, you'll still hit 3 pins. It'll just be a different 3 pins on the LM. So you'll still get that swapping benefit.
I think you'll have to take that offline and show it to me after.
And then in addition to that, you would also get the benefit that when you do that swap, you would change timing. You get, like, you swap maybe the fast and the slow pins.
You're going to have to show this to me afterwards, because I think this is too complicated for me to absorb there. This exact pattern sort of decouples the decision of how do I route to the input of the LUT from how I route to the output. And if those decisions are coupled, then it's more complicated. So I don't have to do this. Xilinx doesn't do this. Xilinx has a more irregular pattern still. It's more depopulated. And therefore, they, if they want to swap the outputs, they have to actually put another mux structure in there. And that's what they choose to do. So that's also a valid thing to do. Okay, so what were their results? So they found for best results, so they take a bunch of switching out of here. Okay, they reduce the amount of muxing inside the logic block. And they found for the best results that they should actually increase the number of inputs. Okay, this is like how many inputs are coming into my cluster. And by best result, I mean get the most area efficient architecture, right? So combine the parameters that are going to give them a high routing completion rate with the least area. Why do you think that it was good to increase this number of inputs that comes into the cluster? Any thoughts? So it basically comes from I've taken a bunch of flexibility away from here. And I saved a bunch of area for doing that. So it was a pretty good idea. But routing has gotten harder. If I add a little bit more flexibility in terms of actually having more inputs coming in, I basically reduce the probability of routing blockage. Especially because the cluster in Airflow was still allowed to use, like if I had 30 inputs, it might sometimes use all 30 inputs. If I saturate the inputs to this thing, like I use all 30 inputs, the probability of getting blocked when I've removed some switches in here becomes much higher. But if they say the cluster can use 30 inputs, but I'm going to build 34, I'm not going to tell it I have 34, right? The extra 4 are my secret, right? It becomes much less likely that you'll get blocked. It's a lot easier to get 30 signals through something that has a peak routability of 34 than it is to get 30 signals through something that has a peak routability of 30. So they could have equivalently done this, probably, by not increasing the number of inputs, but just telling the cluster to use fewer. That probably also would have worked okay. So that's another principle of basically trying to, like, for all these little sub-problems, if you can leave a little bit of slack, like the router still has a bit of breathing room, it makes the overall routing problem a lot easier. So yeah, in the clustering problem in FPGA CAD tools, if you could bring in a maximum of 30 inputs, you usually don't tell your clusterer that. Or you tell it, only do that if you absolutely have to, right? Otherwise, don't go above 26. Because 26, you got some wiggle room, right? It's much harder to get blocked. So what they found is they could actually remove 50 to 60% of the crossbar switches, cut their mux size by 2x or more than 2x. They could, in terms of the whole architecture, so not just the logic block and local routing, but the general routing, everything, they got 10 to 14% area reduction, and it didn't cost them any delays, so it was all good. It did take longer in the router. Okay, the router has a more difficult problem now. Before, when I had a full crossbar here, the router could just come up to here and stop. Like, once it got a signal into the logic block, it's kind of done. The crossbar can do anything. Now it can't do that. It has to go into the logic block through this local routing and choose a LUT input. So it has some extra decisions to make. That expands the size of the routing problem, so it increased the router runtime for them by 2 to 7x. So it's not free. Okay, so the Stratix paper that I talked about also looked at this. So prior Altera architectures did use local crossbars, but they were fully populated. So Stratix, we also looked at depopulating them. And we actually found that 50% was also good. We could take half of the switches out. We didn't get as big an area reduction. We got 7%, and we took a little bit of a delay hit, 1%. So it's pretty close to what Lemieux and Lewis found. The reason we found a delay hit is basically architecture modeling. They were modeling all the LUT inputs as the same speed, and they're not really the same speed, right? The one that's furthest down the mux tree is significantly faster. As you start taking switches out of your local crossbar, your router may not, it has more constraints on which LUT inputs it can hit based on which routing path you're taking, and because they're different speeds, there can be some impact from that. But it was small, right? So there's a little bit of delay hit, but a big area reduction, so this was done. We also looked at less than 50%. And it actually worked pretty well from an architecture experiment point of view, but it became difficult to lay out. So sometimes you get into layout issues too, where something that's more regular is just easier. So we didn't go any further than that. Yeah. I mean, you could make it 25% and still make it regular, right? You just, remove 3 out of every 4 switches, but in a very regular pattern. So you could do that. What we found is that when you looked at how the metal and the transistors were interacting, it was difficult to get an area savings from that. We could remove a bunch of switches, but we'd become metal limited. So it would reduce loading a little bit, but that wasn't giving us very much speed. And it did make the architecture less routable. Did make it harder to hit the fastest LED inputs, so that actually cost some delay. So with a very detailed area model of looking at how you really lay it out, we're not actually going to save it anymore by doing that, so we won't. Does that make sense? But to see that, you had to go pretty far down in the detailed modeling. Okay, so the last slide I'll show before, I think it's the last slide I'll show before a break. Okay, yeah, take a break after this one. Okay, so Intel's latest FPGA is Agilex. It's at 10 and 7 nanometers. There are versions of both. And I mentioned this earlier, but let's come back to it. Their local interconnect is more complicated, and it's because of metal resistance. So metal resistance is getting bigger, even for relatively short wires, because inside the logic block, we really can't use those fat wires, right? We're reserving those to go long distances. So we've got to connect up what's inside the logic block with pretty low-level wire, where we've got a lot of it. And that's becoming resistive, like noticeably resistive, even for fairly short distances, the kind of distances you get in the logic block. So they've basically got 2 different kinds of local interconnect now. Some that only spans like 2.5 of their ALMs or BLEs, and some that spans the whole height of the logic block. So as I mentioned before, it's kind of like another level of hierarchy in the block, or a partial hierarchy. So the local interconnect is getting a bit more complicated to deal with metal resistance effects. This paper also talks a lot about layout effects on general routing, which academic tools are not great at studying yet, right? So if somebody's looking for a PhD thesis, come see me afterwards. So I see Amin is smiling, so he's in. So yeah, historically, architecture research in this area, including mine, has mostly focused on, what's the pattern, how many switches, let's estimate how much transistor area. But as your wire resistance is becoming a bigger deal, you're really looking, and capacitance has always been a big deal, but it's becoming an even bigger deal. You really want to have a switch pattern that keeps all the internals of those muxes small, right? Like there's a bunch of internal wiring that's implied by that, and you want that to be small. So Agilex focuses a lot on how can we make patterns that have reasonable routability while really keeping our connections inside those muxes local. And that's one of the things you're doing here, is you're basically saying, well, I've got some local wires that only span 2.5 ALMs. So those wires are short and the switches are local. They also, when they talk about the general routing, like the routing that goes between logic blocks, all FPGAs really run it over top of the logic block. So it's not really beside it, it's on top. And they basically most of their switching is they take each of these 2.5 high ALM units, so it's like a quarter of a logic block, and most of the wires will switch within that bundle. Okay, so you don't get switching between wires that are kind of far apart in the channel. The majority of your switching is wires that are kind of close together. And I haven't shown the vertical wires here, but basically there's a lot of complicated layout that happens. You get vertical wires that kind of go onto little horizontal stubs, and it's the same idea. You'd have a certain group of vertical wires that have horizontal stubs, and you connect to those ones. They also increasingly, for the wires that go between logic blocks, want to get on one end and get off at the other to minimize via stacks, even for fairly short wires. So less getting off in the middle to minimize the loading on the wire. And to compensate, they make essentially more wire lengths. And I can't remember the exact numbers, but I think it's, maybe Isidore knows, like 1, 2, 3, 5, like there'll be a whole bunch of different wire lengths because they're generally trying to get off just at the ends, right? So you want a bunch of wire lengths that together get you to where you need to go, so you want to get off at the end. Yeah.
So quick question about the long lab lines. Why, I'm not entirely sure, like, why do we need to have long lab lines as opposed to just hard segmenting it and say we have the 4 lanes, right? But then
Yeah.
get rid of the long lab lines because they basically make the structure like kind of like a weak hierarchy, and now you can't do like swapping between these 3 lanes.
So I can't give you a definitive answer. I guess one of the reasons would be that you will get some connectivity that goes, you're not going to be able to cleanly partition your design into just 2.5 ALMs that talk to each other and they don't talk to these other ones. So you are going to get sometimes, even after the CAD tool tries to say, keep this ALM closest to the one it talks to the most, sometimes it's going to go, I need to talk to somebody down here. You're also sometimes going to have a signal that comes in and it's like an enable signal for a decoder or something. And it turns out it goes to like 5 or maybe even all 10 of these. Now, if you only had short wires, you'd have to have, okay, you bring it in 5 times and you get to all the places you need and you'd have to push that back to the previous muxing. And you could do that. That is an alternative.
Like the input to the block by everything else.
Yeah, you might have to like bring it in 5 times in 5 different inputs. So, but that is costly as well. That's like I've just burnt 5 muxes and in the end I still had to drive 5 different pieces of metal. So at least in Agilix, I'm not on the team. You're actually probably you're closer to the team than I am at this point. But my guess, and it's a pretty educated guess, would be that, well, because of those reasons, they went, we don't want to get rid of all the long wires. They still work. They're slower than these short ones, but they're still not that slow. So let's keep some of them because we still need that. If you didn't do that, probably what you'd have to do is have the ability for these short wires to drive each other. And you'd essentially maybe start building like a small island-style FPGA inside your island-style FPGA. But that has its own challenges, right? Like at these low levels, hierarchical has worked pretty well, right? Like when you have a very small group of things, it's pretty fast. So yeah, you can't say that there's no other solutions, but just taking all the long wires out, or the full logic block height wires out, they have to put something else in to kind of mitigate that. Does that make sense? Let's talk offline. Okay, so let's take a break till 5:43. I'm going to steal back 2 minutes. I was going to quickly see where I am, actually. Cool.
I was trying to draw the picture before. There's some pattern, and you're going to have the same pattern down here, which is what you were showing before.
Yeah. All right, okay.
And they'll connect. So basically what I'm saying is, let's say the first one connects like this. The second one, I'm basically saying you do this.
Connect offset by 1.
Yeah, and then basically the same pattern here. And so what you're guaranteed is because of the permutability of the mux, right?
Of the
these
LUT.
are
I see.
these are logically equivalent.
If it's a LUT, yes.
Yeah, but because these pins are different speeds, you can now potentially get a speed up just by swapping these two, which you couldn't get before.
Yeah, it's interesting. One thing I neglected, just because it's complicated, is if these aren't LUTs, like if I put a carry chain in, or in practice I actually have adders in here too. So in different modes, different groups of pins are swappable. And I also sometimes lose this output swappability. Like if it's a carry chain, I can't do it because swapping it around would break the carry chain.
Yeah.
So for those ones, you can't swap them. And I think the fact that like different groups, like it's not always 6 inputs that are permutable. Sometimes it's 5 because it's fracturable. Sometimes it's these 3 or these to tell you until we're out of time. We used to have 13 lectures in this course, so it's sad. I know it's sad that we only have 12 now. Okay.
Previous year, the extra lecture?
It is actually, if you want to look at it. So I usually change what I talk about as well. But yeah, last year I actually posted the last lecture in case you want to go look at it. It's kind of into different architectures and different things like flash-based FPGAs and soft errors and so on. So, okay, here's another thing that seems to violate one of the principles I talked about. So I said it's bad to have hard boundaries, where you suddenly cross some spot and your delay goes way up. And it seems like we have that. If I want to go 4 units in this architecture, I can use this length 4 wire to connect those 2 red blocks. If I want to go 2 units, that's still my best option. I have to use that length 4 wire. So got some extra capacitance, some extra delay beyond the minimum that physics would let me do. Now you could say, well, put length 2 wires in, and that would make it less extreme. So I have different wire lengths. But I still have to go out of, go through a few levels of muxing to get out of the logic block and back in. Yeah.
So the placer makes it so it always has to be 4 away.
Wait, so you're actually intentionally sabotaging the CAD tools? Okay, so I don't want to do that. Okay, so this seems suboptimal, right? Because I got closer, but it didn't get, maybe got a little faster because the resistance is a bit lower, but the capacitance is the same. You could say, okay, maybe put a length 2 wire in, and that could help. But basically, I still have this problem of when I go out of a logic, if I'm inside a logic block, I use my very fast local interconnect. If I want to leave a logic block, I have to go out on a routing wire, come back through an input connection block, go back through the local interconnect. So it's not a huge step function, but there is a bit of a step function to go just 1 unit over. Okay, there's kind of a hard boundary between this logic block and that logic block. Even if they're right beside each other, I can't make them connect as fast as physics would allow. Okay, so can we do better? And you can. So this is basically a paper by Jonathan Rose and one of his graduate students. I don't want to get into the details of the electrical design, but this is, to look at these things, you usually have to assume some electrical design. So here's what they assumed. You've got a basic logic element. It can feed its own local routing. That's what we've been looking at before. But it also drives out through a fairly big buffer, and this particular architecture is using tri-state buffers, onto a big routing wire. Okay, so routing wires that go between logic blocks are relatively long, they're relatively capacitive. So I connect onto that. I don't really want to go very far. I just want to go to the logic block right beside me. So I now basically go into its connection block input mux. So I immediately go into a mux, and I get into its input pin, and then I'll go through some more local routing. Okay, so even though I only want to go 1 unit over, I had to go through a couple of big buffers, charge a big capacitance, then go through a mux. And that got me from one logic block to another. And it would mostly be the same, it would be pretty much the same if I wanted to go up a few units. So this is pretty much the same delay to get to several logic blocks that are near me. So this one's really close. Maybe I can get there faster. And what they did is they said, sure, let's put an extra connection in. So they took the same signal from the output of the LUT. They put it through a smaller buffer, going, okay, this is a lightly loaded signal. And they sent it straight into the connection block mux of the logic block next to it. So basically what they avoided is some relatively large buffers and a large capacitance here on the routing wire. Because they said, I don't really need to go on that routing wire. That would get me to be adjacent to a whole bunch of logic blocks. I don't need that. I know I just want to go to the one right next to me. So I'm going to build a path straight there that just goes from my output to its input mux. Yeah?
How is this any different from a length 1 direct drive wire?
It's not that different. So if you basically said, what if I had a really short wire like length 1? I mean, this is essentially like truly a length 0, right? It also has no, well, I guess it's 2 things. You say length 1 wire, so I guess you're saying make this not super high, cut it off here. A wire that goes the height of the logic block still has some capacitance. And normally I would still have this, right? I'd have some tri-state buffers or a direct drive mux. So they got rid of one more level of muxing versus having that. and they got rid of this capacitance. And if you didn't have really short wires like that, then they got rid of more capacitance. Okay, so basically they put in the ability to do this blue path. And that's going to cost them some extra inputs in this mux, so it's going to get bigger. And they put in a dedicated buffer, so it's going to cost them a little bit of extra buffering and a piece of metal. That's what it's going to cost. So there's going to be some area to this, but it is a more direct path in this case. So this is a pretty common technique to just kind of break this boundary of if you can get things right beside each other, it's possible to be faster than going out to the general routing. So different companies call them different things, but it's basically local interconnect between clusters. So at Altera, we called these sneak paths, at least internally. I think we didn't tell that to the customers. For the customers, I think it's, I actually can't remember what we called it actually. So Xilinx called it Direct Connect. So I think they had a better name than us because I can't even remember our marketing name. But both Intel and AMD have these structures. So, and this academic study found that they did pay for themselves. It was a 6% delay reduction for 4% area cost. So that is a net win. It's not a huge win, but it's a net win. I guess the other thing beyond this delay reduction, it gives you a higher upper bound on your speed. So somebody who's willing to really hand optimize a data path, kind of go beyond, because they're taking a bunch of benchmarks, running them through CAD tools. This actually kind of increases your roof line of somebody who's really willing to deeply pipeline, micro-tune and design, can go faster. So this says it's a win. For those who really want to optimize, it'll probably be a bigger win. So it exists in most commercial architectures. So Altera, Intel do this. Basically, a logic block or RAM block or DSP block can drive not only its own local interconnect from an output in the cluster, but also a few signals, not more than a few, but a moderate number of signals can be driven into the local interconnect of the blocks to its immediate left and immediate right. So it does bypass like any general routing, just goes straight into the local routing of the other one. Does make their muxes a little bit bigger, but because they limit how many signals can do this, it's not too huge. And it's symmetric. So for this particular block, I can drive left or right, and I can be driven from the left or right. Xilinx calls it Direct Connect, and they don't do just 2, they do 8. So they say, well, I got 8 things that are pretty close to me. I can drive all of those with essentially a smaller number of signals. They kind of distribute, how many signals do they want to pay for, but they send them to all 8 nearest neighbors. Okay, so this is a hard question, which probably Isidore knows the answer to. Can anybody guess why the 2 companies did this differently? But often companies and academics just do things differently for random reasons, right? Like there are multiple good solutions. But in this case, there's actually a good reason why this makes perfect sense for AMD, but actually does not make sense for Intel. So it might be difficult to answer. So it looks like I might have even confused Isidore, which is like my journey as a professor is complete. I've now confused everyone. So yeah, it's pretty subtle. So I won't expect anybody to know it, but it's kind of interesting because sometimes if you know what's going on behind the scenes, you can infer what's happening in the architectures. So a really interesting thing about Altera, Intel's FPGAs is they're repairable, okay? And AMD's aren't. So what that means is in the larger, more expensive, this isn't true in like the Cyclone class FPGAs, they're generally not repairable, but the Stratix class, Agilex class, they have big die sizes. So the odds of a defect landing somewhere, making the die useless, is reasonably high. So what Altera does is when you buy, so if you buy a chip that has 100 rows of logic, that's what you can see in Quartus, it'll really have 104, okay? And that means that you can have up to 4 broken rows and still sell that chip. And that increases yield a lot. The way that, and it's actually very tricky to do this because you don't want to sell people a bunch of different chips where you say their timing is different, you need to recompile and so on. Academics have proposed that before, but it's not practical. So FPGAs, people do their design, they validate it, and then they set up basically a manufacturing line to go make a whole bunch of boards that have this FPGA on it over and over again. And there's nobody sitting there running Quartus or Vivado on the production line and madly trying to close timing on every single chip, right? So this would not be good. So what Altera does is basically at manufacturing test time, one of the nice things about FPGAs is that you can test them really well because they're reprogrammable. Okay, so you program a whole bunch of stuff in it, you find all the defects. So they figure out this row's broken. That's programmed into non-volatile fuses on the chip, so it knows that row is broken. And basically the programming hardware, when it programs in, will program not that row now, it'll program the one above it with exactly what that row was supposed to do. And it shifts every row up by one. And the routing is identical, okay, for every single row. So when you do this, all your routing works. And the vertical routing, if you think that the chip has length 4 vertical wires, it doesn't really. What it really has is length 5 vertical wires, okay? So every wire can actually reach one longer than Quartus would ever tell you, which means it can still reach, if there's one broken row, it still reaches past it. And basically the programming hardware can shift the bit stream, and the chip will be programmed with up to 4 broken rows. They can't all be on top of each other. Basically, each broken row protects you. Basically, for every 25 rows, you make one spare one typically, and you can handle up to 1 defect in those 25 rows. And it's invisible to the end user. Does that make sense? So, but what this means is that your vertical wiring is fundamentally more expensive than your horizontal wiring. It's always 1 unit longer than you told the end user, and you have to, there are a couple ways to do it, but the basic way to do it is you make tri-states on the vertical wires. Okay, so they can actually be driven by 2 rows. Okay, so you can't use a full direct drive on it. There's actually a way to do that, but it's super complicated, so I'm not going to tell you that. The basic way you would do it is you make 2 drivers. That actually makes your vertical wiring more expensive. And if you were to make this structure in an Intel architecture, so these ones are fine, right? These are horizontal connections. If this row is broken and you shift up by 1, they all still work. You don't need to do anything special. If you have a vertical direct connect like this that goes up 1 row, in an Intel architecture, you would also have to make another, you'd have to actually make that wire go 2 rows up. Okay, but the whole reason you made this wire was really short. You were going straight into the local interconnect of that one above you. Hopefully you were going from the top of this block to the bottom of that. Because of this need to be able to skip over a row, you'd have to go an entire block above that still. So that vertical wire would become a lot longer, and you'd get some extra muxing and so on. So it's possible to do, but it's just not worth it. So basically you'll see that in Altera architectures, they prefer to do things horizontally. And it's because horizontal is cheaper, because the redundancy always shifts only up. Yeah?
So is that why it's length 24? Instead of like, why is the 16 the vertical one and 24 is the long one? Is it just that kind of orientation?
Well, it does affect a bunch of things. Because of the fact that there are a bunch of interacting things. Because of the fact that now this makes vertical wiring more expensive, like a bit slower and a bit more area intensive than horizontal wiring, you'll notice that Intel architectures also have wider horizontal channels than vertical, because you can actually tell the CAD tools, to a reasonable degree, if you tell the CAD tools they have more horizontal routing than vertical wiring, it can change the placement to be biased towards horizontal wiring. So Intel does that. They actually prefer to make more horizontal wiring than vertical. You can go up to about 2 to 1 before the CAD tool starts, you notice significant effects, and it just can't fix it enough, so you need to add more routing. But up to about 2 to 1, it's almost area neutral, right? It would be best to make them exactly the same, but it's not much different. And because the horizontal is cheaper, that's what Altera does. That's part of what tends to make the logic block, asymmetric, right? Does that make sense? You now go, well, I prefer horizontal routing, and if I make it non-square, my horizontal routes all get shorter, so that's kind of nice. So there's a bunch of things that push them towards a non-square logic block is actually well suited to what they're doing. So, yeah. No, they don't have repairability. So I'll show you something, probably not today, but they get a certain amount of repairability using interposers. So it's a different technique. It's not as powerful, but it gives them some repairability. It's in their most recent big chips. This is something that was very secret for a long time in Altera. Okay, like, well, no. It's been revealed. I've like talked about it before in keynotes and things like that. So, and I'm not the only one. But once it's revealed, it's revealed. So it's like patented. Some of it's quite complicated. It's actually one of the reasons that Altera also liked hierarchical FPGAs. If you have hierarchical FPGAs, it's actually easier to make them repairable because you have a whole region where all the wires end. And basically, you can say, okay, in this block of hierarchy, I told you I have 13 rows, for example. I really have 14. And that's actually obvious how you keep the timing and everything the same. It's just kind of like all the wires span 14 things instead of 13. For Stratix-style architectures, it's actually much harder because all the wires are staggered. It's all irregular. So this was one of the big challenges when Altera bought RightTrack. We didn't want to do a repairable architecture. We're like, no, these island-style architectures, it's all irregular. That's best, and we shouldn't make it repairable. It's too hard. And actually, the chief operating officer just said, "You shall make it repairable," right? Like because he came from the manufacturing side of the company. He was an engineer, but he was very strong background in manufacturing, so he did not want to lose this. And we did figure out ways to make it repairable, but it was actually really hard. And so I think it's because of that it's quite hard, and it does impact the architecture. You have to take it into account in all sorts of ways that Xilinx, AMD have never done it. And it was interesting. There's a case where so I gave you the example of the CEO saying take out meta layers, and I thought that was a bad idea. In this case, the chief operating officer just saying you will make it work was actually good, because if we had not been given that directive, we wouldn't have made it work. Like we definitely had all sorts of excuses of why this is way too hard. We're not going to make it work. And sometimes you just get, I don't care, you're going to make it work. So, yeah.
Solve this problem separately as, by adding a layer of hierarchy. To basically say, when I make my chip, instead of one big monolithic fabric, I'm making a bunch of big but not too big, FPGA blocks that I'm just going to paste together to make my bigger FPGA. And if you want to cross between those two blocks, there's a bunch of fabric to fabric connections that are perhaps not as plentiful as the ordinary routing. So you basically just design a big sector, and then you design the edges of that sector. And now if the sector is broken, you just throw away that one, put a new one in place.
Working for AMD.
Yeah, that might be doable. I think you'd have to draw it for me. So another company that uses this technique, but it's not exactly the same, is who's heard of Cerebras? So Cerebras is a company. They've got a big office here in Toronto. They make this wafer scale engine. So if there's time in next lecture, I'll show it briefly because it's kind of an interesting architecture that has certain FPGA-like aspects. But their most recent wafer scale engine, so it's an entire wafer. It's like 12 inches by 12 inches, costs $1 million, dissipates 45 kilowatts, 900,000 processors. And so they use repairability, right? So they can, and it's connected by sort of a bus-based FPGA-style interconnect, like a spatial interconnect. And you can't yield that thing. Like you can't yield 900,000 perfect processors. So they use similar techniques to basically shift around broken things. They've never revealed exactly how they do it. It's not entire rows. They can go around individual broken processors, which is intriguing. So I don't know exactly how they do it. But so actually a really interesting thing is how you make chips repairable, right? It tends to be hard to do it in a way where you hide it from the end user, especially as the chip gets more irregular. But it can have pretty big results. So anyway. Okay, so let me talk a few more quick routing tricks. Speed unbalanced routing. So a minority of your circuit needs to be fast. So this is something that I did quite a few years ago. And it's basically I electrically changed the design of some wires. This is an architecture with all length 4 wires, but I just electrically, by spacing out some wires, essentially reducing their capacitance, I made some of them faster. And what I found is that this is the average speed of a bunch of circuits. After I made 20% of the wires faster by spacing them out and reducing their capacitance, I had pretty much all the speed gains. You only got a very little bit after that. And I found this in a bunch of different circumstances since. So if you have why do you think this happens actually? So it's again, the router works well, right? So it says the router finds the critical paths and puts them on the fast wires. And it doesn't need everything to be fast. So this is a technique you can use in lots of places. Try to make a fraction of your architecture extra fast, and the other parts you can make more area efficient. This is a similar technique that we used in one of the Stratix ones, Stratix 2, so it's in the paper on that. Basically, this is kind of a complicated figure, but this is a routing driver. So it's basically one little inverter, big inverter, level restorer or weak keeper. And then these are SRAM cells. And this is a 2-level mux, okay? That's taking a whole bunch of routing wires. So that's all basically a redrawing of things that I did on the whiteboard. But there's also one fast input here that goes into just through one pass transistor. So for this, all these other routing wires, like this routing wire here, I go through this pass transistor and then this one. So I go through 2 pass transistors, 2 levels of muxing. This one only goes through 1. Okay, so we've made an extra fast input. And what this paper points out is that by making one fast input to the routing drivers, you get about 4 to 5% more speed. So it's quite beneficial. If you keep adding fast inputs, you're eventually just going from a 2-level mux to 1-level mux, which we saw costs area. And it also starts slowing, like basically the mux is getting more metal, so they're not quite as fast as they used to be. So this is another technique you can use, but you can only do it for, kind of a few things, 1 or 2. We used it for 1 fast input. And we tried to pick the input that was most used. Okay, so if you can think of, okay, you actually profile the architecture to figure out what's your most common connection path, put that one on the fast input. So do you think this will combine, can I combine this with that wider metal spacing for more speed? So what do you think? This is somewhat unanswerable, right? Like you could argue either way. So I guess the answer is you can try, but you do start getting some diminishing returns. So the router's pretty good at finding the critical paths and putting them on the fastest resource. But if you start kind of making all sorts of, well, this one's a bit faster this way, this one's a bit faster that way, eventually the router just can't handle all those constraints. So if you do, a lot of unbalancing, it can get so difficult for the router to line everything up that it still works, but you don't get quite as much gain as you hoped for. Okay, so I was going to talk then about Stratix 10. So how many people read the Stratix 10 paper? So 2. So how many people are done all 10 papers? Did you do them like early in the course, or are you just hoping for like a really big finish? How many people are hoping for a big finish? Like 15 or 20. You're at 15 or 20? So Isidore could potentially like sell you like, like could he transfer like paper reading credits? So actually, I'm pretty sure that our academic integrity policies don't allow me to create some kind of marketplace. So we'll remove that from the live stream after, just in case anyone from the administration is watching. That was a joke. It's an interesting paper. So I've left it open, I think, till this weekend. So if you haven't gotten to 10, try reading a few of these last papers. Okay, so what's the motivation for? So big change in Stratix 10 is that they push registers into the routing, okay, which is a really big change. So the motivation was the designs are becoming more register rich, and you can't cross the chip in one cycle. So if I've got to go a long way across the chip, I have a bunch of paths that are like register, a wire, and then another register, like no logic in between. And you get a lot of those. And actually you can have this like with 6 registers and over again to get all the way across the chip, or 10 registers. It can be a lot. And an FPGA can do this. You have registers inside your logic block, but there is a delay to get in and out of the logic block. You go through a connection block into your local routing, you get into the register, then you go through your output connection block or some switch block to get out of the block again. So at 28 nanometers, Stratix 5, this overhead was about 300 picoseconds. So it'd be a bit smaller than that in the latest process nodes. It's not like a catastrophic overhead where you say you just can't do that. But if I'm trying to run at, 700 megahertz, well, let's say in this chip, 700 is probably not reasonable. But let's say I was trying to run really fast, 500 megahertz. I only have 2 nanosecond clock period, and I'm pipelining to keep my paths well below 2 nanoseconds, because I don't want to have the place and route system must be perfect. And I'm kind of burning 300 picoseconds of that 2 nanoseconds every single time. It's going to make me have to pipeline deeper. And then maybe that's annoying. And then also maybe I start running out of registers in the logic block, because the deeper I pipeline, the more registers I need there. And maybe I can't get them exactly where I want them too. So maybe there are some in a logic block, but that's not good enough. I need them to be right here because I need my placement to be very, very well done. So the idea of Stratix 10 is, well, what about adding registers to the routing wires themselves? In order for this to make sense, we're going to have to do it with low cost, because if we add a lot of expensive hardware, this is not a good idea. And we want them to be fast. So we want the registers to be quick, because if adding those registers in the wires, is not significantly less than 300 picoseconds insertion delay to get in and out of a logic block, well, then that's not really worth it either. Okay? So that's the idea, but there's a bunch of circuit constraints. Okay, what's the costs? It's harder to use registers in the routing. Okay, so those registers in the logic block, we have all this muxing to get to them, which means we can kind of get to them from anywhere. The registers in the routing are going to be connected probably to an individual routing wire. They're harder to get to. There's more chance of wasting them. It's going to change our CAD flow and our architecture in a pretty big way, so this should not be a tie. Actually, one of the engineers who used to report to me at Altera, actually I think he gave an estimate that's very, very high of exactly how much effort they put into this. But I think he probably doesn't want the number to be public. But it was a lot. This is many, many person years of work to make this work. Well, many tens to hundreds of person years of work. There's going to be an area overhead because we're going to be adding these to a lot of routing wires. And we'll have a slight slowdown in the routing switch delay. So if we add anything to the routing circuitry, it's probably going to make it a bit slower. So there's going to be some negative feedback. Yeah?
About the first point being harder to use, that's assuming that you're doing it during placement. Or wouldn't the typical flow would be a retiming flow? It'll just be, I happen to be going through this register, and if I moved it, I would get a better performance. So
Ideally, you want to do it on placement.
Well, I guess what I mean by harder to use, more probability of being wasted. If you build so many of them that you can get them anywhere, then I guess you can say they're not that hard to use. But if you built them in a limited number of places, they're kind of harder to get to, because how do you get to them? You get to them through the routing network. Does that make sense? So and they are also harder to use because this is kind of skipping to what they did. To keep the cost down, they built simple registers. Okay, so simple registers, they don't have clock enable, synchronous clear, asynchronous clear, etc. So they are somewhat harder to use because if you have those extra signals on your register, the routing ones are simpler and they can't do it. And then they have CAD techniques to say, well, maybe we can redesign your logic in front of the register so you don't need a clock enable anymore. And sometimes you can, and sometimes you can't. Does that make sense?
Yeah.
So
it's just like if you were using them as a normal register where your placer is going like, okay, I'm going to put this in the routing, that's obviously not going to work.
Yeah.
If you go with a flow where your placer says, I'm putting this inside of the logic block, and then your router does a path, and then after you're done the routing, you go, okay, well actually, my path happens to go through a register, and my register happens to meet the, synchronous clear, whatever requirements. So I'm just going to move that, which was previously in a logic block, and now it's in the routing.
I think this is still harder to use, right? You're basically saying the CAD flow kind of ignores them till the end or assumes they're going to happen and tries to use them later. That's still harder to use. In fact, in Quartus, so in Quartus, Stratix 10 has an enormous number of registers, okay? So skip ahead, but it's basically got registers at every routing wire. So it's an enormous number of registers. With at least the default CAD options, if your design uses more registers than are in the logic blocks, it won't compile. And the reason it won't compile is Quartus has to first put them in the logic blocks and then later stages say, this particular register could be moved to the routing and it's beneficial to move it to the routing. So that kind of tells you they're still harder to use for the CAD tool. If you actually pipeline so deeply that you exceed the logic block register count, the CAD tool doesn't know what to do with it. Now there is an option to say don't do that, which one of my grad students tried on that H-pipe design, the high performance CNN accelerator. The help says this option may reduce design performance and increase compile time, and it did exactly what it said. So that just says it's challenging, even for the CAD engineers. And that does make it, yes, usable, because he would have actually liked to pipeline so deeply that he exceeded the logic block register count, but the CAD flow couldn't support that in a very optimized way. Anyway, that might be getting too far ahead. But anytime you add something new, like something like a routing switch, there's going to be some cost. So there's going to be some slowdown. And then how do we get the clock to these registers? You think about a logic block, it kind of groups together clocks and all sorts of signals. Okay, we put registers in the routing fabric. Where does the clock come from? Like other routing wires? Like where did it come from? Okay, so what they do they do a very clever thing to get these registers. So first, they don't actually build full registers in the routing because it's expensive. Whoops, what happened here? Okay, I guess you guys can still see it. That's good. Okay, so let's start with like, what does a regular register look like? How many people, do you remember back in like 241, if you took your undergrad here, did they teach you like, the weird edge-triggered flip-flop with all the cross-coupled gates and stuff? Or did they teach you master-slave flip-flops?
Master-slave, but then if you take a 300 level course, they do teach the other.
Okay, the other one's useless. Okay, so don't take that 300 level course. And that's on video. I don't care, Bruno. Okay, so great. I like Bruno, so it's even better. So the way you really build it is like a master-slave register, which is nice because it's also much easier to understand, right? So what do I have here? I have a latch. That's what this is. And when my clock is low, let's see, when my clock is low, I'm enabling this tri-state. So my data flows into this node. Okay, let me get rid of that. When my clock goes high, this is cut off, and this is enabled. So now I just hold this value. Okay, so this latch is holding my value when clock goes high. When clock goes high, my value can propagate out through the second latch. Okay, so it behaves, this master-slave, your data comes out on the rising edge of the clock. But it's because of the sequence of when these latches become transparent. So how many people have heard of a pulse latch? Okay, one person. Okay, so a pulse latch is, what you do is you basically get rid of one of these latches. You just delete it, okay? And if I'm going to build a lot of these latches, which I'm going to do if I stick them in I'm basically sticking them, what they do is they stick them in the driver, the direct drive driver of every routing wire incorporates the option of using one of these registers. Okay, so that means we'd like to make this as cheap as possible because that's a lot of spots. So a pulse latch gets rid of one of these two latches. And then what it does is you don't use the clock, you don't use the inverse of the clock. What you use is use a clock pulse. It's basically a clock edge pulse. Sorry, my writing is messy here. If I have this on the next slide, but basically if at the rising edge of the clock I create a short pulse and I put that into this control signal, basically my latch accepts new data just in a narrow window right by the clock edge. And after that, it just holds it. And that looks an awful lot like an edge-triggered register. In fact, if I make the clock pulse infinitely narrow right at the edge, it is an edge-triggered register. Now, I can't actually make it infinitely narrow because if I do that, I'm going to get capture failures. So I can't make it that narrow, but I can make it pretty narrow, right? I can make it a small, this is something you have to think about carefully, but a few hundred picoseconds I could certainly do. So it approximates an edge-triggered register. Okay, so why is that good? Okay, it's smaller. I got rid of one of the latches. It behaves like a fast register. Now, why do I say it's a fast register? So if you look at the Quartus timing report, you'll see at the start of your timing pass, you have something called TCQ. That's clock to queue. Okay, what is my delay when the clock hits till the data comes out here? And you'll see at the end of the timing path, there's a setup time, which is my data comes from D, how long till it gets in the storage node. The sum of those two things is approximately the delay through this structure. Okay, so you can move around where you put the setup versus the TCQ, but fundamentally it's like the delay to get out of one latch and the delay to get into the other latch. And you can kind of shift around how you account for those, but basically getting rid of one of these latches is going to make the sum of TSU plus TCQ smaller. And those things are added into every single transfer, so it helps you. It doesn't help by a huge amount, but it helps some. Then the other thing is this pulse. So I'm making this pulse. Okay, so I've got a clock that comes in. Here's my clock. And I'm going to have to build some circuitry to generate a pulse right around the rising edge of the clock. I want it pretty narrow because I want it to behave a lot like an edge-triggered register. If I intentionally make that circuit widen out the pulse, so I'm making it wider on purpose now, I also can do what's called time borrowing. I can keep the latch transparent for a little longer, which allows me to essentially make the timing constraint going into that latch a little easier. Okay, but I think I've actually gotten onto my next slide. So is everybody with me for this? There is a cost. There's a pool or hold time. So let's go back to a narrow pulse. So let's forget about time borrowing for now. I make this pulse. Hold time is I'm not allowed to change the data basically during this sampling window. Okay? So I can't have a path. I don't want to have some other register that got activated by this same clock edge. I don't want its data to propagate here before this latch goes opaque, because that would basically, that's a hold time violation. A hold time violation actually means you got next cycle's data today, all right? And that breaks your design. So if I make this pulse too wide, I start getting hold time violations all over the place. It's like my shortest paths are my problem. Okay, so that's my cost, is this register doesn't have a very good hold time. How do you build this? So basically, I already showed you this. You build one latch instead of two. You build a pulse generator. Pulse generator is not that complicated. So it basically takes a clock, it delays it through some inverters. This is actually a programmable delay pulse generator. So basically, I delay the clock, I pick which delayed version I want, and I negate it and AND it with the original clock. And what that is basically it's going to give me a pulse when there's a rising edge. Okay? And if I choose the very little delayed version of the clock, it's a narrow pulse. If I choose a more delayed version of the clock, it's a wider pulse. Okay, so I get that. I wouldn't want to build this pulse generator for every single pulse latch because it's bigger than building the other latch. But if I build a few of these and share them across a lot of pulse latches, I can save area. Okay, so that's shared. Yeah, I guess I already talked about this. So this programmability is what they do in Stratix 10. They make the pulse width programmable. There's two reasons for that. Like if you're guessing how wide you need the pulse to be, and you're doing that before you've got a lot of chips back from a new manufacturing process, you'd like it to be as narrow as possible so that you don't get a lot of hold violations. But if you make it too narrow, the chip doesn't work, right? Like it doesn't capture. So the nice thing about FPGAs is you can say, well, make it programmable. And the CAD tool will choose. We'll test a whole pile of chips, and we'll tell the CAD engineers never use a setting lower than this. So that's one reason to have it programmable. The other reason to have it programmable, though, is it lets me now make wider pulses. And I guess, as I said, what the wider pulses do is allow you to borrow time. Okay? So I have a register here. It's going through maybe a LUT. It's going through some wires, and it's going to another register. And let's say the data path delay is 2.2 nanoseconds. And my clock period is supposed to be 2. So this is a setup violation, right? This doesn't work. It took more than a clock period to get there. If I increase the width of this by 200 picoseconds, or if I want to be safe, maybe I'll put a little margin, 300 picoseconds. Basically, this register, which is really now a pulse latch, it doesn't just capture data at t equals 2 nanoseconds. It actually lets data through all the way up to, let's take 300 picoseconds, 2.3 nanoseconds. So that means it actually works, okay? Now, it ate that from the downstream timing margin. Okay, this means that, well, the next register better need, it only really has 1.7 nanoseconds of time now. But there are cases that happens reasonably frequently. This guy's got a bit of margin. This guy's got negative margin or negative slack. We can actually shift what the capture window is by changing the pulse width. Does that make sense? Now, I do have to watch for, let's say there was another register up here that also went into this LUT. And let's say that path from here to here to here is pretty fast. Let's say that path is, well, let's say it's unreasonably fast just to make a point, right? Let's say that path is 200 picoseconds. Then I can't do this, okay? I can't do it because by allowing this to capture data for another 300 picoseconds after the clock edge, this guy changes at the clock edge, his new data makes it all the way through this guy and into the downstream logic. That's the definition of a hold time violation. You just broke your design. You didn't write your design saying, maybe this data changes in this clock cycle, or maybe it changed one earlier. I don't know, right? So that puts a constraint on this hold time constraint would mean you can't do this. But if this guy, let's say it was 200 picoseconds was pretty fast. Let's say really this path was 500 picoseconds. Okay, now it's okay again, right? 500 picoseconds is more than 300. I can widen this pulse. I still won't get a hold time violation. Okay? That was a pretty messy diagram, but hopefully that's understandable. Does everybody understand that? One of my favorite questions on a PhD qual is I actually give people a circuit where I have setup and hold violations to see if they can analyze it. Many of our students actually do not fundamentally understand how setup and hold works, but that is how it works. Setup is you must get there in 1 clock period, and hold is you must not get there in 0 clock periods. That's the fundamental meaning of them. Another nice thing in FPGAs that make these pulse latches attractive is well, FPGA routing is relatively slow, but in this case, that's a good thing. If I actually took that 200 picosecond path and I told the router, try to make this slower, use an extra wire. Like 1 extra wire will probably add another 200 picoseconds of delay. So I can actually fix that hold time problem by telling the router, make this a bit slower. So that's actually nice. And this I already talked about, the insurance policy part. Yeah.
I noticed when we read the second paper, the Anderlecht paper, they got rid of this and used normal flip-flops. So was that partially the insurance, or just they knew that?
So I'll talk about that in a minute. So I've actually got that after these slides. So hold that question, okay? Okay, so this is just another picture. This is from the Stratix 10 paper. It's basically, this is a direct, okay, so what is this? This is a direct drive routing switch. Okay, I've got a mux made out of pass transistors or maybe transmission gates. I've got this weak keeper, okay? I've got a small inverter, I've got a big inverter. That's my direct drive switch. Okay, but then they add some things on it. And what they add is shown in the dotted lines. So they basically add the ability to tri-state this. That's what these latch enables are. And they add an entire latch, okay? So they can basically tri-state this so that this can form a latch, and they add another latch here. The combination of those things is that this routing driver can be programmed. If you basically turn on this transistor and this transistor, then it just behaves as a regular routing driver, okay? Like this buffer turns on, this buffer turns on with slightly degraded speed because I've got an extra transistor in my pull up and pull down paths, but it's on, this node's not the most capacitive. So if you're gonna add extra transistors in your pull up and pull down paths, try to do it on a node that doesn't have too much capacitance. So that's their speed cost. There's an area cost because they added a bunch of transistors, but they point out in the paper that this transistor is big, and the transistors they add are small. So the area is not as bad as you think. Also, there are a bunch of transistors in here. Okay, so and then they also have to add some shared circuitry. So they add basically a little bit of control circuitry and a pulse generator that they're going to share across a whole bunch of registers. So in the end, they say that this increases the area of the logic block plus the routing, okay, so the whole thing by 5%. So that's not catastrophic, but it's not zero. But they also say it doesn't include the clock pulse generators and this little bit of control circuitry. So we don't know from the paper exactly what the area overhead is, but it's somewhat more than 5%. Does that make sense? So it behaves as a regular routing driver, but also now can be a pulse latch. One of the challenges, well, how do they get the clock to this? So like if they build a whole other routing network to get the clock to every routing driver, this would be kind of madness, right? Like the area overhead of that would be catastrophic. So the paper goes through how they do this, but they basically group a whole bunch of these routing drivers together. And they do a bunch of studies on how much grouping can they do. So they take 50 of these routing drivers and group them together, and they say that those 50 can pick between 2 different clocks. Okay, so that's what I'm showing here. And there actually are 200 routing drivers, so they do this 4 times for every logic block tile. They also do the same trick in the local interconnect. And there they say all of the local interconnect wires, like the input, that's what this is showing here. This is like the local interconnect driver. All of those have to share the same clock, okay? So they basically reduce the clocking flexibility to keep the cost reasonable. Let me plug this in because I'm going to lose power. Why do you think they do less clocking flexibility for the inputs to the logic block? They can basically put a pulse latch on that. Essentially, it's on the local interconnect wires. Why do they have to all share one clock, whereas the routing drivers, they make 4 groups of 50. Each group of 50, you can, every one of the routing drivers can pick between 2 clocks. Yeah?
It's more likely for a lab to try to use the same clock that is for the routing to use different clock.
Yeah, so that's a good answer. So basically, the logic block has related logic. The cluster has tried to put things that are related together, so it's highly likely that it uses one clock. And even if it doesn't, it's not that big a constraint to say, well, you can only use one of the clocks for these registers. The routing, you've got signals that might have come out of this logic block, but you've also got signals just flying by that may have come from far away. So you need a bit more flexibility in the clock because those other signals might be using different clocks. So they put more flexibility in, but they didn't have to put too much in. So by using this structure, it's still not too expensive. A key trade-off parameter they go through in the paper is what's the hold time, and they don't 100% know. So at the architecture level, they basically did studies of how much, if the hold time's worse, they basically can't use these pulse latches as much. Like if you have like just one routing wire driving another routing wire, and the hold time, the pulse width is reasonably wide that you had to use, you're probably not going to be able to turn the pulse latches on both of those because you get a hold time violation. So how effectively they can use these is impacted by what the hold time of the pulse latch itself is. And so they did a study of that, and they showed if it's really small, under 200 picoseconds, it doesn't matter much. If it's pretty big, like 500 picoseconds, they actually can't use nearly as many of them. They have to start using one every 2 or 3 wires, and it costs them frequency. So in that case, like 14% of their clock frequency. And these are on designs that they've basically pipelined deeply, right? So to make maximum use of this architecture, you pipeline the design early, and you turn on retiming to let the CAD tool move the registers around a lot. Okay, so to summarize this, there's a 5% area increase, plus some extra for the clocking control. They don't say what that is. There's a small routing slowdown, but they don't say in the paper how much that is. So it's small, but we don't know exactly what that means. We get a lot more registers, and they're reachable without this logic block insertion delay. So we can retime logic more aggressively, more flexibly. Like before, we could only retime logic by moving things, from this logic before this LUT or after this LUT. Now we can move it after this wire or before it. So it's kind of more fine-grained. And we can pipeline more deeply because we've got so many registers. So in the paper, they claim that on designs that they don't redesign, they get a 45% speed improvement. And if they redesign them to basically pipeline more deeply and a few other techniques, they get about a 92% speed increase. Now that includes a technology improvement. They've gone from 28 nanometers to 14 nanometers in other architecture gains. So you can't figure out exactly what gain came from this. My guesstimate is it might be 30% with deep pipelining, which is pretty significant. And that's a guesstimate just based on how much gain you would typically get with this kind of process shift. They also need new CAD tools. So this really is targeted at designs that are deeply pipelined. So the CAD tools, they added a lot of features to Quartus to tell you, here's where you could pipeline more. We talked about how loops limit your ability to pipeline. So Quartus would identify loops, tell you this loop is in the way, can you get rid of it, etc. And they integrated retiming more deeply in Quartus. So with Stratix 10, the design is retimed before placement, after routing. So there's so many registers, and they enable a big enough performance that they use retiming multiple times, trying to get the registers in the right spot. Okay, so So Stratix TED works pretty well, right? So some of my students have gotten good frequencies from it. But if you read the Agilex paper, which is 10 nanometer, so the next generation, they backed off some. So they found that in Stratix 10, the hold time that they had to meet when they got the chips back was such that they couldn't turn on 2 pulse latches on consecutive wires. Okay, so I have, one relatively short wire feeding another relatively short wire, and so on. You couldn't turn on a register on both these. Okay, so that puts some constraints on the CAD tool, just because the pulse width, minimum pulse width they needed was wide enough that this was too fast. They could get a hold time violation. On top of that, when they went to 10 nanometers, the wire resistance went up, which meant Agilex uses more short wires. More short wires means more routing drivers, which means that you're going to get even more registers, but you found you couldn't use them all before. So what they did is they basically said, okay, well, maybe that was too far. We're not going to use as many registers. So they put them only on about a third of the wires to reduce area. By doing that, they found that they didn't have to use pulse latches anymore. They could use full registers. And that makes their hold time better. So they went back to, okay, we'll use the more expensive registers, but we won't use them in all the wires. And that's going to give us better hold time, and we're happy. So they kind of did 2 different variations on this theme. Okay, and maybe I'll go like a couple minutes over to what does Xilinx do? Okay, so Xilinx is an area where AMD and Intel don't agree. So I know that like the chief architect of AMD's chips basically says they've studied this and they don't think you should do this. Okay, but clearly Intel does. So this is a case where the 2 major vendors don't agree. But Intel or AMD has done something to respond to this. So what they did is, so in older AMD parts, much like Intel parts, you have registers after your lookup tables. So your lookup table, and I'm showing here they've got 2 registers. They can register, if they make this into 2 5-LUTs, they can register both outputs. Okay? What they did in Versal, their latest chip, is they also put registers, which are optional. So that's why I'm showing there's a mux. You can register or not register. They put them on the inputs of the block as well. Okay, so does this seem useful? Yeah, what do you think?
I would say yeah, 'cause it's kind of intuitive from a programmer point of view. When you make your module, you just need to make sure you register your inputs and register your outputs. You could get something like this.
You can. Okay, so they've increased the depth of pipelining. Now the thing is that this is actually kind of unbalanced though. Like the delay of a LUT's not that big.
Right.
So let's say, I don't actually know exactly what it is in Versal, but let's say it's 250 picoseconds would be a typical number in a couple of process generations earlier. Well, say in Versal, I bet you the LUT delay is like 150 picoseconds or so. And the delay to go through a few wires, depends how far you go, but that's usually going to be the bulk of your clock period. So they can pipeline more deeply, but all they've cut out is essentially the delay through the LUT, right? So the wire delay is going to tend to be the larger part. So it's imbalanced. But then what they did is something clever, is they said, well, what we'll do is we'll put programmable delay units on the clocks, okay? And by doing that, let me show you what it is. Okay, so they have this nice picture in their paper. Here's their original, this is like a timing path. So they're basically showing I've got this register feeding this register, and then that register feeds this register. Okay, so they're showing 2 timing paths. And my original critical path would be this, 1.8 nanoseconds, right? Because that's the longest path in this very simple design. So if they retime this by saying the registers that were on the output of the logic go to the input, well, they're saying the delay of the LUT and whatever's in the CLB was 300 picoseconds. So they were able to retime, and they get a somewhat better critical path. Okay, they get it down to 1.6 nanoseconds. I don't know how they got 1.6. This is 1.5. Oh, I see. This side is 1.6. Okay, so they're limited by that. So they've retimed. They've made use of the fact that they can move this to the inputs. They get a little bit better critical path because it went from here over to here, and that's 1.6 instead of 1.8. Then they say, well, but I could use all my registers. If this is a deeply pipelinable circuit, we'll tell the designer pipeline more deeply.
So turn them all on. This one, this one, this one. Okay, and now that is 1.5 nanoseconds. Okay, they're limited by this critical path. Here, I'm going to circle the critical path. And then the last thing they do is they say, okay, well, I can shift the clocks with those delay chains. So I shift the clock to the input registers, and basically I delay all the other clocks and I don't shift it. So it effectively cuts up this timing path. It doesn't actually physically move the register into the interconnect, but by shifting when I clock it, I can do time borrowing. And logically, it's inside there. And once they've done that, they basically equalize all these delays, and they get a minimum clock period of 1 nanoseconds. Does that make sense? So it's a clever trick. And let's see. Okay, so pluses and minuses. Versus Stratix 10, at least, is less area. Should be less area. They added registers on the inputs, but that should be less than putting them through the interconnect. They claim less timing overhead. They slow down the block inputs, but not every routing wire. They can make these registers full-featured. So one thing that sometimes makes the routing registers harder to use in Stratix 10 and Agilex is they don't have clock enables and A clear and so on. These registers are full-featured. It does allow deeper pipelining. They get kind of 2 spots to pipeline now instead of 1, but not nearly as deep as Stratix 10 or Agilex. Okay, so they do wind up. So it's a less intrusive change. It doesn't enable the same degree of extremely deep pipelining. And then they use this clock skewing circuitry to essentially time shift, what they call time shift the flip-flop, so that from a timing perspective, it's as if it's in the interconnect. But they can put only one register in the interconnect that way, right? Like they got one input register. They can move its clock around so it divides up the input interconnect path. But they can't put like 3 or 4 or 5 registers in that path, which Agilex and Stratix 10 could do. Okay, and that's it for register routing. Sorry for going over time. So I'll be up here in case you guys have any questions. Thanks.